Alhamdulillah.
Nice of you too, very
Charlie, I can describe the future. He will raise his hand.
well. Surely, fools.
No, 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 no sort of thing. He will lift his hand. No, see, he shown the lad. Shown the lad.
But this one is great.
Uh, Hey boss, shut down with you. Let us listen. Wait. Yes.
Pero ahí
No pen?
Microphone.
The one right here.
Ah, the one to right here. Okay, okay, okay.
And the microphone.
So, the one to right there.
Can you use a microphone? The microphone? Okay. On this, on the tools. The drawing tools, yeah. Okay, perfect. Right. Okay, can you hear me? Okay, so really, I apologize for the delay. Sorry for that. What we will do today is louder. Like that you can hear me? Yes, okay. I can just talk more in the microphone. Okay, so what I will do today is just finish the Grover algorithm because we left the Grover algorithm a bit suspended, and then talk you about how some applications and how you can treat a chemical system, what can you do, and something related to more to research and looking for improvements. So, as you remember, you have n qubits, and you have some ancilla qubits. So the Grover was first doing this, then having here, of course, you have many lines. Then you have what we call it the oracle with phase marker. Oracle space. Yes, let's say plus phase marker. That means that you not only recognize which is the state that satisfies your oracle, but you also change change the phase of this state. Then you have again another Hadamard gate, and then you have something that we didn't design, but we have to do it now, which is kind of conditional phase shift. Or is called also diffusion. Let's say that this diffusion operator can amplify the solution amplitude. So diffusion. And what is doing this operator is that it's also, if you have the zero state, remember when zero state, I also mean extended to all qubits. This is going to zero. Now we will see this in detail. And then all the other states are just get a phase. Okay. Goes to minus x. And then we have another Hadamard. So this one is the Grover operator, and is the one that every time we apply, we let the coefficients of the solution be bigger and bigger. Okay, so every time you apply this, the coefficients of the solution get bigger relative to the others. Okay, how this is possible? How we can write such operator? Okay, so let's consider this operator here. Okay. So what is doing this operator? This can be interpreted as a reflection on the zero axis. Why? Because if you have if this operator is applied to zero, what do you get? When I mean zero, I mean also zero to the n. This is just reproducing zero. Okay, so this vector is not changing at all. But any other vector get a phase because it is orthogonal to this. So if there is another vector which is not zero, when I apply this operator, like to a generic vector x, this is zero, and only the identity with minus will act on a vector which is not all zeros. Okay, so if it is applied to an x, it will generate a minus x. So if you think this is really like having a reflection, a rotation, Yeah, but a reflection more than a rotation. Because it's like I rotate everything, I reflect everything along one of the axes, which is the 0, 0, 0, 0, 0, 0 axis. Okay. Okay, so if we put all together, because you remember this is the operator, this one is this operator here. Let's say this one. This one is this operator here. Why this is not okay? Right? Yes. Okay, like this one is this operator here. But then you have the Hadamard here, the Hadamard there. So the Grover operator is not only this. So we have to put all together and see what's happening. When you put all together, we have Hadamard to the n, and then we have 2, then we have 0 to the n, we have 0 to the n, then we have minus identity, and then we have also again Hadamard to the n. Okay. Okay, so if we write psi as the equal superposition state, that means Hadamard to the n, which is applied to 0 to the n, which is 1 over square root of n of sum over all the bit string of x. Then we can write this operator. So this is therefore psi when applied to this. Okay. And then I can also have this like h. So we have h to the n. So 2h to the n, 0 to the n, uh, 0 to the n, and Hadamard to the n. Minus I. Okay, so this is just 2 psi minus I. And this is the full Grover operator. Okay, so we have drawn this, but we want to understand how this operator will act then on a generic state. Because actually it will start acting on the equal superposition state, because it will start acting here. You see, we start with the equal superposition state here, and we repeat this acting many times, this action many times. So if we start acting like that, then we have on a generic state alpha, what is the behavior? So this is just a generic state. Okay, so Grover is 1 to the n, 1 over n. Two, sum, you have a double sum here, of course. I and j, just following the definition of psi, minus, the identity can be seen in this way. I don't know if you ever met this. You know that this is the identity or not? Did you ever seen that? Yes? Who? Okay. Good. Okay, so the Grover operator, when it acts on alpha, someone is not very happy about the Grover operator, but I can understand his point of view on this. So this is 1 over n, 2 sum of over k, sorry, sum over, not k, this is sum over I and j. And then you have I, and then you have j, and then you have the alpha, which is sum over k, alpha k, k, and then you have sum over I and k and k. Say k, that's another thing. Sum over. Okay. I and k. And we have I, and we have I, k, and then we alpha k. Okay. So, of course, this is delta jk. This is delta ik because they are orthogonal. The basis, orthogonal basis. So you might end up with this. So we have to shift again up. So you end up with G applied to alpha is equal 1 over n, 2 sum over k, alpha k, sum over I, minus sum over I alpha. Okay, so what is this value? If you look at the sum over k, well, this is just the average, the arithmetic average of the coefficients. We can call this like average of alphas. Okay? So that means that the Gruber algorithm over a generic ket alpha is working like that, is summing over I minus alpha I plus 2 times the average of alpha. Okay? So what is actually this operator? What is doing? It's inverting something, but it's inverting something around an average value. So if, for instance, the coefficient of the ket alpha I is equal to the average, it's not doing any change, because if this is the average, then if alpha I is close to the average, then this also is the sum of minus average plus 2 average is just the average. So if any ket is has coefficient, any coefficient is very close to the average of a whole coefficient is not affected by this operator. If it is not, it is affected. So how this is doing? So we can see the Grover operator acting like that. I would like to draw this kind of picture here. So you imagine you start from psi, And when you start from psi, psi is the equal superposition state. So you have all the weights which are at the same of the same magnitude. So this is, let's say, alpha 1, this is alpha 2, this is alpha 3, alpha 4, and so on. Okay, so all weights are the same. And each one of these would be actually 1 over square root of n. This is the beginning. Then, after that, we applied the oracle plus phase marker. That means that we apply an operator that select the coefficients that satisfy the oracle, I mean the state that satisfies the oracle, and just change sign at its coefficients. Okay, so that means that after having applied this one, remember this, after having applied the oracle here, so we have two parts, the oracle and then the diffusion. So far, we just draw the diffusion because the oracle, we were discussing about that before, okay, last time. What is doing the oracle? The oracle is just checking which is the solution of your search and changing the phase, putting a -1 to the coefficients of the solution of the search. Okay. And then we have to apply this diffusion. So what I will do now, just graphically, is just to show how this step, the oracle step and the diffusion step, will act on the starting point, which is this one, which is the equal superposition state. So you have the equal superposition state, which is this one. And then you have to apply one step, the oracle and phase shift, and one step of the diffusion step. So when you apply the oracle and phase shifter, what we will do, we will get would be something like that. That all the coefficients remain exactly the same, but the one that match just change sign. Okay, let's say this is alpha bar. And all the other will stay as they were before. So in this first step, all these other are 1 over square root of n, and this is -1 over square root of n. Then we will apply the Grover operator. The diffusion operator, and the diffusion operator is just flipping, inverting above the mean. What does it mean, inverting above the mean? That if what is the mean of these values? The mean of this value will be very, very close to here. It would not be exactly here because one of them has minus sign, but will be more or less very close to that. Only 1 out of n is shifted. Okay, has the opposite sign. So that means that if we have to invert around this. Okay, so that means that everything will remain more or less unchanged, because not exactly unchanged, but more or less unchanged, because 1 over n is very close to the mean, except this one. If you have to invert this is then inverted. So that means it's inverted around the mean. So that means that this would be like that. Okay. It's just a rotation around the mean. If you, yes, rotational symmetry, okay, reflection, yeah, thank you. Reflection around the mean, Okay, then you have all the others which are exactly the same. Okay, so then let's go to the next step. But the next step, I will apply again the operator. So I will apply again the selection. If I apply again the selection, then the oracle will select, will let them unchanged all of this and will invert this. Okay. And then there is always this inversion around the mean. The mean is more or less this one. And so this is then going up and growing every time you apply. Okay. Okay. Then you can. I mean, we will not do it, but you can show that you need to reach actually when. Of course, you cannot repeat it. So what is happening is at a certain point, this will become the dominant one, and that means that basically all the coefficients are almost zero except the one which satisfy the oracle, which is almost one. Okay, so when you select one of the cards out of this you remember the library, no? So at the end, in the bunch of cards, all the cards will be the same, basically. So as soon as you get anyone, you will read the correct. You find your book because all the cards were transformed in the one which satisfy the condition of the oracle. Okay, so you see how different quantum algorithm may be. I mean, this is something that has kind of geometrical interpretation. We use the phase. We use some way an iteration that is repeated several times, and it's anyway an algorithm which is probabilistic. Okay, because at the end, you will have very high probability to get the one, but never 100%. Okay. So I think that, are there any question on this? Is there any question?
Right, and if you play G here,
Yeah.
is that the diffusion operator?
It's all the operator, yeah.
Diffusion operator.
Yes. In this notation, yes. But actually it should be the old operator. Yes, but in this notation is the diffusion operator. Okay, I think I have. I need the passcode of the meeting. I don't have. Oh, you have. Okay. Yes, just password.
Illustration.
Nine one five.
So 757.
7576162. Thank you.
Yes.
So, in short, But what is this problem? So, okay, now it's fine. What do you need? Okay, thank you. Remove this. Okay, so so the answer choice is interesting, and hardware efficiency are very short sequence. You lose the physical meaning, and you can work on these variation parameters. You have seen probably yesterday how you can choose optimizations, and now these optimizers can be different if you have noise, if you don't have noise. Basically, there are two different kinds of optimization. You can improve the wave function either at the gate level. So that means that you can change the gates, change the parameter at the gates, or you can either work at the pulse level. So forgetting about real gates and just work at the pulse level. There is also some work in this respect. So you can encode the variation parameters directly as hardware is doing. This is even shorter in some ways because it's closer to the hardware. Okay, we'll just tell you some project example, mainly about algorithm and something about application. So there is some application, but this is just to show you that there are also companies like any compared pharma company, algorithmic software company in quantum computing, which are also interested in learning something about quantum computation and to collaborate. Okay, so first we start with this idea that I want to share with you. We had some time ago. Basically, we have this idea. The eigenvalue of the orbital operators are invariant under unitary approach. So if you yes. Somewhere in the having short sequence, it helps anywhere, anytime you have noise. Because applying a gate 1,000 times and the gate has noise, it's actually then of course it depends on the hardware, the kind of noise, but this is always effective. If you have on the other side, if you have but we don't. So if you have a fault tolerant quantum computer, then even if some qubit fails, then it's survived in some way. Okay, it can be maintained and you can run as long as you want. So getting a shorter means also, of course, get less time. It's like saving CPU if it was a classical computers. So it's always better. So the idea was the following. But what about if I do a rotation of my orbitals? Or actually, not really a rotation of my orbital. If I change, we like to see this in the perspective of the operator, not on the orbital. So if I use this operator instead of this, the results are exactly the same. Okay. So any unitary transformation is not changing eigenvalues of any Hermitian operator. So the idea is that what is the idea? The idea is that you can define in some way what is the point? The point is that my circuit in some way is variational. But what is not variable now? What I cannot change is the topology of the circuit. So once I draw this circuit, I cannot change that. Okay. So if I put a synapse between qubit 1 and qubit 2, then it will remain. I can vary this rotation, I can vary this rotation, I can modify a bit everything, but the circuit is still like that. And if my problem would require that it's better to have a synapse between 1 and 8, I have no other chance I cannot do it. I can do by getting longer and longer circuits, because all these empirical circuits are done by repetition of the same framework several times. Okay. So this repetition will include for sure the synapse between this and that one. But of course, I need many. It would be much better. Yeah, it's a bit chaotic today. Thank you. Okay. So so the idea is that in some way the wave function is fixed because it has some topology of the circuit, but what I can do is to change the Hamiltonian or to rotate the Hamiltonian. Okay? So I can rotate the Hamiltonian and I can write in a general way this unitary operator. And let's see if in this way, by just rotating the Hamiltonian, since I have these degrees of freedom more, which allow me to change the Hamiltonian without changing the result of the Hamiltonian, I might have some possibility of getting with the same circuit in terms of topology a better result. Okay, so some derivation can be done. So I can maybe show you directly the scheme of the algorithm. Okay, you start from this Hamiltonian, and the starting unitary matrix is just identical. Okay, then you transform this Hamiltonian into qubit Hamiltonian, which of course depends, and the coefficient here depends on the unitary matrix. Then we will do some normal BQE with fixed rotation. So at the beginning will be identity, and then later it will change. So for instance, the DQE with fixed unitary, we start with the try-work function and how it's working. You have to measure the expectation values of all the terms of our Hamiltonian. You remember that the terms of our Hamiltonian are Pauli matrix strings. So every Pauli matrix string has to be measured, and then we can evaluate the energy, and we can use evaluate also. And we can use several algorithms to optimize theta parameters, which are not just one, there are many parameters of the field. Okay, so this is standard DQE. Once we have optimized standard DQE, we can start to optimize the unitary for U. What can we do is we can calculate the derivative of the Hamiltonian with respect to the parameters of the unitary, and we can measure the expectation values of these Hamiltonian derivatives. And what is nice is that in these calculations there are not much overload. In some ways, many times you will find the same string that you have already measured here. Okay. So the overload here maybe it's a factor of 5 or something, but it's not too much. You can reconstruct the derivatives, and then you have the derivatives, and you can apply different way, adiabatic, non-adiabatic, Newton, different strategies of optimization, and see if the changes in the unitary will help in lowering the energy. So basically, you are changing the Hamiltonian in order to lower the energy of that particular fixed, let's say, variational wave function. Okay. Of course, if it is converged, you are happy. If it's not converged, then you go here, you transform again the Hamiltonian with the new unitary, because here you have to get new parameters for the unitary, so the optimization procedure, and you do one more step. So the hope is that in this way we can try to arrive to a description of the Hamiltonian which is adapted in some way to the empirical answers that we have. Okay, this is just some optimization results. I think you have seen that you have to be careful. All these results that I will show you are results with, let's say, state vector simulation. So we don't, we are not considering noise. We are not using real hardware. For real hardware, I think you can have a look to the lectures from Daniel that is using real hardware or hardware simulations. So this is just to find general way of optimizing. I mean, general strategy. Okay, so what we did here is we wanted to test and see if this is actually something good or not. What we did is that we considered several different kinds. So this is not an end. This is a square. So that means that these are alternative starting points. So we consider a circuit which is done like that. This and these are connected, and these and these are connected, these and these are connected, these are connected, and so on, like a stair. But then we consider also other circuits where maybe it is this one with the second, or this one with the fourth, and so on. So we consider all the combinations that you see here. Okay. In some way, we change the entangler map. Changing the entangler map, it means to change the topology of the circuit, because we want to see if using this strategy we can actually arrive to a solution that is not depending on the topology. Usually, the variational solution does depend on the topology of the system, because if in your physical solution wants to have a correlation between this and this, then if this is missing, you have to pass through other qubits, and it's not so efficient. Okay, but in this case, since you are rotating the Hamiltonian, it may be that it is getting better. Okay, so in blue, sorry, in the green, you have the normal VQE as a function of the rectangular map index. So you have 145 rectangular maps, and we run 145 different VQEs. So all the different VQEs are here. This is the energy, and this is the correlation energy. The correlation energy is the difference between the Hartree-Fock energy and the exact energy. Okay. So 100% means exact, and 0% means Hartree-Fock. Okay, Hartree-Fock is the starting point. So what you observe is that you have, you see how the VQE's results do really depends on the entanglement mapping index. Okay. So if you might have this, you might have this, you might have this, and only few of them reach two or one, I don't know. Here I see something greenish. So only few of them, only one entanglement map reach 100%. Okay. But this is because, because of what I said before. Because maybe the system prefers to have this particular entanglement map, and you have to find that. You don't know this before. You have to, you have to be lucky. Otherwise, you need more and more repetition of this, which is fine, but then it's much more complicated to optimize, because the number of parameters depends linearly on the size of the circuit. This is only the entanglement map, but remember that you don't have only entanglement map in your variational circuit. Your variational circuits are done like that. So they have entanglement maps, but also rotation. And these are the parameters that are optimized. So every time you add a bunch of anytime you add one of these stairs, you have to add a rotation, and then another stair, another rotation, and so on. So it's true that you will reach anyway the results, but with much longer circuit, that means more noise, but also means more difficult to optimize. Because many parameters, function you have seen, I think, yesterday, are very difficult to optimize, especially in presence of noise. Okay, what is happening with this battle? So this is wave function adapted Hamiltonian to orbital rotation. With this battle, what we did is that every one of these points is starting from the green one. This is the green one without battle, and then it goes down because, of course, you have more parameters. It's true that you have more parameters because now you have the parameters of the rotation. But this doesn't necessarily mean that you have more parameters at all, because maybe with the parameter of the rotation, you need less repetition of the circuit. And what is nice is that now we obtain much more stable, at this point here, much more stable values, lower value in the average, much lower value in the average, and much more values that arrive to 100%, or close to 100%. Okay, so we want to see if, for instance, all these results is really the same wave function or not, or there are different minima in some way. Okay, so we can check it, and it turns out that they will function with the same energy, represent really the same physical state. Okay, so it is the same physical state, which is represented by this. Of course, they are different because the rotation is different. But if you see them in the same basis, they have the same physical state. So like one is in from one basis, so the coefficients are different, the other from other basis, the coefficients are different, but actually the physical state is almost the same. It's very similar in the same basis. Okay. Then there is another issue about VQE, which is even worse. VQE has this problem about starting point. So that means that you start, I mean, especially when you use empirical answers, which are the theta from which you start? Random numbers. Okay, you don't have a guess for your starting point. And this is a big problem because very often the initial guess is so far away from the final solution that you really get stuck at the local minima. And this is what is happening. So now we have a fixed topology, like this one. So the topology is fixed, but we repeated several times, 100 times several VQEs. So if you use normal VQE, you see that you will never get better than 40%. But if you introduce additional degrees of freedom that are due to the rotation, then you get much slower. And you also get something which is close to 100%. So in some way, one other effect of this introduction of Vator is also to be able of being less dependent on the starting point, which is very important when you do optimization. Question? Okay. Okay, what about the number of parameters? Yeah, the number of parameters are actually VQE is about 48 and 56. So you see that you need the depth 5 or 6. Depth is the repetition of the stair C0. So if you use VQE, you need 5 or 6 repetitions of this, and in total 48, 56 parameters, or totally 35, 42 C0 gates to get here. If you use Vator, you just need depth 2 and you reach the same result. And you have, as a number of parameters, something which is less, smaller. So 24 for the answers and 16 for the Hamiltonian. Okay, so a bit less of parameter to optimize, and the optimization which is less affected by the starting point. Okay, then I mean, this rotation can be viewed in twofold ways. Can be viewed as a rotation of the Hamiltonian, or can be also viewed as a change of the orbitals. Okay, you always have this double interpretation. So if you look at the which are the orbitals, so if you attribute this rotation to the orbital instead of the Hamiltonian, you will find out that the optimal orbitals, so the wave function adapted, let's say, orbitals. When I talk about wave function, I mean like the hardware, empirical hardware. so the topology of the system. So these are the best orbitals that fits the topology of given system. And they are quite different. Okay. They look different. So, and what we observe, this is, I don't know, this is a bit of quantum chemistry, so I don't know how this is understandable by everyone, but it has been shown since 1955. It has been conjectured that there are a special kind of orbitals where the quantum state is expressed with the least number of determinants. This was a guess made by Ludwig in 1955. Okay. So that there are special orbitals that are the natural orbitals, which are diagonal, the orbital that diagonalize the one particle of the density matrix, the ground state, and he claimed that these orbitals are the ones that really can help in having compact wave factor in some way. So not many determinants. Okay, and we have looked at our orbitals, and they look really as the natural orbitals. Actually, the overlap is very high. Here we have 0.99%, 0.97% of overlap. So it seems that it's actually what this battery is doing. Okay, it's finding again natural orbitals. So the Vator orbitals are actually natural orbitals. Okay. Then we continue to think about how to design these empirical answers. So all what I will say today is about empirical answers. Okay. So one good thing is to rotate the Hamiltonian so that the problem adapt to the topology of the answers. A second point is that we would like to observe which is the correlation of between qubits. So, and the quantum model information can capture this correlation between qubits. So it's a measure of the orbital correlation. So the correlation between one orbital and the other. This is a map. This is how to read this map. 0, 10 are the orbitals. So there are 10 orbitals. 0, 10, there are 10 orbitals. And then the spot is blue if there is no correlation, and it's yellow if there is high correlation. So there is high correlation here, 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 and here. Okay. Of course, these maps are symmetric with respect to this line. Correlation between 1 and 5 is equal to correlation between 5 and 1. Okay, and then this is a kind of movie. We want to monitor this correlation and see how this correlation is changing along orbital accumulation, because we have in mind that actually our way to rotate the Hamiltonian should concentrate in some way the correlation on less spots on this matter. So if you see the movie, when you optimize, you see that some spots disappear, and in some way, everything is more clean. Okay, so this was the initial correlation, and then some spots disappeared, and everything is more concentrated. So in some way, this new orbital also concentrate the correlation on less orbital pairs. This can be seen also by, and this is quite general, and this is the same as the natural orbital. Okay. I don't know why it's. Okay, it does take time. I love it. Okay, so like this is so you see there is a bit of concentration, less spot, but more intense. And this is a quantitative graph. So this is the intensity of as a function of the cubic pair index. So basically, this is the number of spots, which is 64 for another system. And this is the number pair index, and this is the value of the matrix. So when you have Vator state in converted basis, which is the Vator one, you see that the correlation has some tail, some steps, and then it drops to 0. So basically, we are able to concentrate the correlation in less cubic pairs. If you do like everything in antiphone basis, you have like a double of correlation. Of course, the more correlation, the more spots you have, the more you have to connect the qubits in the circuit. So it's very good to have it concentrated. So the idea is, can we use this information for an empirical answer design? So shall we use this fact that, wow, the correlation is concentrated, so I can design the answers just to reproduce this correlation? Of course, this is a bit strange because if you don't know the solution, you don't know the correlation. And then if you don't know the correlation, you cannot design your answers. Okay. But the idea is how can we design an answer from quantum motor information? The idea is to use a, let's say, lower level quantum chemistry method to get some correlation in math. MP2, so not very expensive. And then starting from this correlation map to draw the answers. So for instance, if here, here you have just to have a look to this and this. They look pretty similar. So one is the solution, OCI, and one is actually made by MP2. So, for instance, MP2 calculation can ask you to identify important spots. If you are doing, this is on natural orbitals. We understood that they are the orbitals, the part of the type of. If you look at, in this case, this is much more spread because these are antiphone orbitals. Okay, so the idea is, yeah, we have the correlation map, how to design the circuit according to, so the idea is do some quantum chemistry low level, let's say, find the correlation map, and from the correlation map, design the circuit according, and just putting correlation between only between the qubits or mainly between the qubits which are connected. Of course, you have many choices. There is a problem of, I mean, you have many choices to join this. Okay, like this one, this one, then this is 0 with 4 and with 5, 0 with 4, 5 with 6, 0 with 5, 0 with 6. So everyone who's this spot correspond to a kind of synod. There is a kind of arbitrariness in the order of this synod. This we cannot avoid. We have done some study, but it's a bit arbitrary which synod should be before, which one should be after. Okay, I will not go much into the details. So the difference in ordering, yeah, it's important. but of course, but not extremely important. And this is some result. How to read this plot? As I told you, BQE has to be repeated several times. This is a very simple wave function, so we are not going to achieve 100%. That means the exact solution. But we get better than RT4. So RT4 is 0 and X 100. Here we are reaching like something like 50. Okay, so it's a very poor wave function, but because it's short series. But this is a comparison between the Boolean tangled ladder and which is very expensive on the quantitative calculation, and KIDA. KIDA is this technique. And as you can see here, for instance, so this is KIDA, and this is the depth, so the length of the circuit. So if the circuit is, for instance, 3, the wider, the more BQE result in this range. So that means that with that 3, you have for all the KIDAs, the higher probability is getting something like 50%, and you have also some probability around 20%. Probability, why? Because you have to repeat the BQE with several starting points. Get something. I try to say, but it is like that. But if you use like Boolean tangled ladder, you are always here. So very often you cannot move from RT4. This Boolean tangled ladder basically has 0. This is a bigger molecule. But then if you use KIDA, you arrive at 40%. So in some way, it's a nice idea, the one to look for correlation map and draw the circuit according to this correlation map. But as it's not solving anything, it's not solving everything. This is just some schematic way. So the ladder empirical answers is it's some way good, but it has to stop at some energy. The quantum chemistry spiral adaptive answers, it's very complicated, it's very long. And in some way, KIDA is a very cheap solution, very effective, but of course not as effective as the quantum chemistry empirical answers, which is much longer. Okay, we went more, so we were thinking, okay, how can we prove that? Shall we, for instance, put as correlator not only the C naught, but something else? Yes. Here, for instance, we have implemented as correlators fully SO4. So it's full rotation, parameterized rotation of 2 qubits. You can, of course, you have more parameters, but then you can get shorter circuits. This is working. Let's say it's working to get a reasonable number, but it's anyway very tedious to arrive to a very good number. So it's working to have a rough wave function. It's very quick, but it's not the best if you really want to arrive to 100%. Okay, so this is the main result. We also have extended everything to KCCF like scheme. I don't know if you have seen what is KCCF. The scheme with Billiard. Oh, you know. So another strategy that can be used in quantum chemistry is, okay, full CI will consider all the excitation. Okay, but these are really a lot, and maybe it's not so meaningful an excitation that goes from here to the orbital up there. It's shouldn't have physically a good a weight in the wave function. So why doing that? In this way, you can reduce the effective space by defining several different regions. One region with an occupied orbital, one region with the active orbital, and another with the neutral orbital. So what are you doing is that you are considering virtual orbital always empty, occupied orbital always occupied, and active orbitals, and you solve basically you solve your problem only here. Okay, this is much better because even because this can be smaller, and so you throw away some part of the phase space which is not meaningful from the point of view of I mean from the physical point of view, and you might have much more accurate result with the same effort. Okay, so maybe I will not use 2 hours because we were already late, so I will try to finish it before. I just want to show you, okay, some results. These are dissociation curves. So that means that these are, this is, for instance, the nitrogen distance, and these are the exact, these are our result. Okay, the red one. So reasonable, not perfect, not spotted on the top. Of course, this depends a lot on the system. Nitrogen is the hardest chemical bond that you can find. So it's very correlated. It's a triple bond. It's very difficult. But anyway, we got a car which is rather good. Okay, just to show you some application of why any would be interested, because there are polymerization for plastic and rubber materials, which have been done currently using different catalysts. The most common catalysts are Ziegler-Natta catalysts, and then there are the new generation catalysts which are working on free radical polymerization. So the goal would be to study this reaction, study the reaction not fully, but with the scheme of CAS-SCF that I have explained before. So just restricting the study to the important active space that take part of the chemistry. Okay, so I don't care about the one and the 2s, the 1s orbital of the carbon, but they will not take part in the chemistry. So I keep it fixed, and that's it. These are like some chemical reaction. I mean, of course, this is example of a radical polymerization reaction. So these are two monomers that comes together and form a polymer. No one. where the bond is not shown, but then it should be there. So we use a really minimal active space for doing that, and these are the results, which are encouraging. The red, the results that we have reproduced from the literature. And this is our answer. So we decided to, in our answers, to put a fully rotation. So these are fully parameterized 4x4 minus rotation. Real rotation. Okay, this is some results. You see that we got very good, 96%, 99%. So we were able to get to the point on this reaction step, but this is not. So this is we got very good, but it's not working for everything. As far as the system is getting bigger, we cannot catch all the chemistry there, because of course then the active space becomes large. And these are the orbitals that are included, for instance, in the active space. And they are different when during the different step of the reaction. So the reaction occurs, you have different orbitals, and you have to select these orbitals because you want only the active space being the occupation number to vary. Okay, this is also some. Yeah, as you see here, we are doing good, but we cannot reach 100%. So still a lot to improve, and we are working on that. Okay. I think, okay, this is another application on drug discovery. So they are interested, this pharma company, to drug discovery. And one of the most important points was to have reliable geometries. So what we did is we implemented, actually it's still ongoing, but we implemented a way to also to optimize the geometry, not only the wave function, but also the geometry, so that everything can move. And this is done from a technical point of view, very advanced. You have different ways to parallelize, to use high performance computing, where you have you can parallelize on message passing, you can parallelize on shared memory way, and in a different way. Just a few words about this. We have developed a software which is called Quark, which is Mathematica Lapida, which is in-house. Why having another software, yet another software? I mean, the reason was that we wanted something which was really specific for chemistry. So in some way, we took from many other libraries what we like, and we put them together. So it's a software which is good if you want to develop new algorithms for chemistry. So this is the aim. It's good because you have only what you need. Okay, if you're doing in Qiskit, it's huge. You get lost immediately. If you work on this, it's every new algorithm is like 50 lines, and you can use pieces that are already there. It's documented. Of course, you will have the slide, and you can download it, and you can contact us if you are interested. We were thinking about doing some tutorial on that on 19, but maybe probably it's too, I don't know, too complicated too, because you're still learning quantum chemistry, quantum computing. So the tutorial will be on simpler cases. Okay, So thank you. And that's it. Other questions or curiosities or? Yes. Yes. Yeah, sure. I mean, if you are in already, if you have already an answer, so which is especially the starting point is already in some way the correct in the correct direction. Yeah, then it's in the funnel of computation is much more defined and you can go faster. If you have any way to, I mean, this affects also in some way in indirect way. Because if you are an answer that is missing some connection with qubits, then you need more more repetition to arrive at the same goal. More repetition means more variables, more variables means slower conversion. Any other question? Okay, so maybe, I don't know, Daniel, we should let them 10 minutes break or, yeah, okay. Thank you.
Much.
Yeah.
I found it so interesting. This is so nice. And I don't know, can
Yeah, sure.
so nice. I mean, you don't have to give me the just give me the PDF. Sure.
Yes, yes, yes.
It's so great. I mean, but I don't want to shoot now. But I just a little bit ask you some questions.
I understand your. Right. Discussion. This is easy like Thomas.
Yeah. That's great. Yeah. So can I ask just one? You need to correlation also. You know, you say certain things are correlated. But how do you find out?
Yeah, we use lower level quantum chemistry to find the correlation.
Oh,
So
it
it's
means
a
you
bit
do it on
tricky.
classical.
The classical
And
computer,
then you,
but
you program it.
yes, yes. Yeah, I mean, I think it is nice, but then what's happening is that you get very short function, very quick, but then if you want to have 1%, it's big. So you get very easily something done.
Yeah.
That's very difficult something.
Yeah.
But this is reasonable.
Yeah, this is like basics.
If you
If you are
have
very
a strategy,
determined,
yeah,
it takes very long to
if you
learn.
have other strategy,
Mm.
maybe in the long term, then we like building the circuit, which is an adaptive to strategy. But like that, you have your circuit, you start from a simple circuit, like start from any from no circuit. Okay, and then you consider your gate in a pool of operators.
Yeah.
You have a pool of operators that can be independent. And then you consider the circuit of all these pool of operators, and you calculate the gradient energy, and you choose the one which gets lower energy. So in this way, you build step by step your circuit. It's
I
much
see.
lower,
Yeah.
but then you arrive at the end.
Oh,
Much.
that's
It
interesting.
takes
So
more
we are
time.
talking about ansatz.
Ansatz. Yeah,
Okay.
it's only ansatz.
I see. And the gradient is classic. The classical.
Yeah.
Yeah, and I was very curious about, for me, this Hamiltonian of
That's what yeah.
and the I mean, why
change,
is that
change
there?
the perspective.
I thought, whether I moved the state or the.
Yeah. I mean, it's the same way. It's
What is
the same way, but it's the same way as move the state, every day the state.
But it works better.
But in principle, yeah, it would be nice to think that you have to adapt to the state, which is harder and change the connection. So you adapt the problem.
You have to
I mean,
to a state.
in some way, of course, it's the same as you rotate these orbitals, huh? But I like to think that you have to adapt the problem. The hardware is the state. It's the connectivity.
Yes, the connectivity.
Yeah.
Yes.
The hardware is the connectivity, and you can change the program in order to adapt to the connectivity of your hardware. With the world. It's the same things, but it's another perspective.
Okay, no, I get it. I think I get it because somehow you cannot change the heart, right? But the gates,
Yeah,
maybe you can rotate them in some nice way. That you rotate the whole thing, but it depends on how many parameters you have.
Yeah, but like this synapse is connected to this, you can change during the optimization.
Yeah.
Unless you don't use this adaptive QE, which is testing several different gates and choosing the one that is better for.
Yeah, okay. So, wow. Are you often in Africa or not so often? Do you come sometimes to Africa or no?
No, never.
Never.
No, it's not first time. I was one in Sharm el Sheikh, but this is not.
Look, if you maybe you want to find it when you're recognize application. And you invite them to come to the school, check the best, creating something, whatever. I mean, you cannot get it. You can take some. Very nice to learn this is what. Or maybe if I just read through it because I have some to do there. Wants to do this, but they don't know. Yeah. And if we will go through this now, analyze it, and then maybe if you ask you concretely, and if you can just step us into read this, and at some point we will be ready to really get something out of your talk, of your if you come.
So I would need someone to tell me again the Zoom meeting, to log in. Whoever knows that.
We can just look at participants. Okay. And then we say invite. And then there is a copy invitation link. Here's the meeting passcode that is already there. And the meeting, this is the number. Okay. So it's 91. I got it.
The meeting.
I got it. 915 8295 8484. Correct. And then the yeah, use my no. Okay. No. Okay, meeting can code again. 915.
Ich habe jetzt das Passwort, das braucht an der Stelle.
Good. 75
Yeah.
71
He's joining the meeting.
62. Again, 75
Yeah.
71 62. 62. Okay. No, Google can what? Okay, meeting passcode 75 75 71 62.
So yesterday was a different one. Oh, no, okay.
Do it. Want to share the screen? The button to share.
Yes, but yesterday I couldn't predict. Oh,
Oh, I
okay.
did, yeah.
The window. Okay.
That's the share.
Okay, so I think we can get started. Last part of my lecture to continue on the quantum computing aspects of how quantum algorithms can be used to solve this dynamical mean field theory based model for correlated electrons. So for solving problems of material science, especially describing transition metal oxides, rare earth containing permanent arc magnets, and similar. Yesterday, just to a short recap, in the morning, I introduced to you the so-called Hubbard model, very famous model from solid state physics, very famous model to describe the interplay that you have on the one hand between the kinetic energy. So I introduced the Hubbard model, which is a famous model to describe the interplay between the kinetic energy of a many particle, many electron system and the Coulomb repulsion. If the kinetic energy, which we describe by a parameter T, which is in this simple model the hopping between sides, the kinetic energy is much, much larger than the Coulomb repulsion. Electrons will not bother a lot about this Coulomb repulsion. They will spread out through the lattice. That is its wave-like character. You get nice electronic bands, you get good electron conduction. On the other hand, if the Coulomb repulsion is strong, that means it prevents two electrons on the same orbital, one will spin up, one will spin down, because they have to pay a penalty. This on-site the action term. So if that is strong, then you will get localization. The electrons will like to stay one on each atom, and they will not hop because it's too expensive in energy. And you get an insulator. So with this model and having those parameters, you can describe transitions between conducting material and a so-called non-insulator, which is insulating because the electrons block each other because of these correlation effects. Then I showed you one method to solve this Hubbard model. I said that in general it's not solved. There are certain parameter regimes where there exist solutions, but it's not solved in general. It's a very complicated model, although it looks very similar. It's very simple. I show that the dynamical mean field theory describes or tries to solve this model in an approach where you can say I single out an individual atom and try to calculate what is the influence of all the rest around this atom on itself. So I describe the rest by what they call a bath and reduce this system to what is depicted here, just one of these correlated atoms. And yesterday we went through many details, the physics of such a simple model of an atom. And it is coupled to a bath of non-interacting states, auxiliary states. It's a model. And we looked yesterday at the spectral function of such an object, of an atom, coupled to other states, to some environment. We've seen how the peaks, that is, the very sharp lines, can call on the blackboard. Look at the spectral function, which gives you the probability of finding an electron at a certain energy or an electronic state when you try to add or remove an electron of the system. So the isolated atom had two peaks, while when it was coupled, peaks broadened. And if there's strong coupling to an interacting path, you would also get in the middle some state. Now, the DMFT approach was to solve this model in some iterative loop. And the connection between the different models was the Green's function, which is directly related to the spectrum. Okay, now let's look at this model that I had on the right, the Anderson impurity model, because that's the model we want to now solve on the quantum computer. So I draw again this picture here. We can think of it in terms of this atom we had yesterday, having the two degenerate levels with the spin up or spin down, and the possibility to carry two spins, but then paying an additional energy of u. That's what we have in mind for this light blue symbol here. I showed you that you can write it in terms of these creation and annihilation operators in such a way where you always have the pair T, D, dagger D. And we have the notion that that's counting the number of electrons. Okay. So D, dagger D was the number operator. And so we have, for example, D dagger D would spin up. This is counting the number of electrons of spin up, which can be 0 or 1. That means you can have here we count the number of electrons spin up and spin down. Here's also the electronic spin up and spin down, and then we do the same path and so on. And this last term, I also showed you yesterday, this always implies moving an electron, let's say here from path side I to dot side. And so the labeling typically in literature is then called is D because this whole theory comes also from solid state physics. So we have quantum dots. We can also just do an experiment and generate such a system, a local artificial atom with quantum dot, which is coupled with so that's why it's D for the correlated orbital and it's C for the band. Okay, so I said we think of this model, this correlated atom, as the model we discussed yesterday for the atom, and we think of the environment as a set of other levels and different energies that can take 1 or 2 electrons, and there's the coupling between those. I said the coupling will lead to broadening and shifting of the peaks. Now there's a problem, because this model, if you try to look at the topology, it would look like this. And I will try to use consistently the colors here to give you the feeling. So we have the correlated orbital, which is the blue guy, and it's coupling to each of the levels individually. So it would be like a star with all the different orbitals that we need to describe the path around it. So one guy in the middle coupled to a lot of path sides. And the problem is, if you look at the topology of a quantum computer, I showed you yesterday, it looks like this, so it's absolutely not a star. Yeah? You have 2 neighbors or 3 neighbors, that's it. The latest chip, you got 4 neighbors. So this is not the best topology to bring it on the quantum computer. But if you want to bring this on the quantum computer, you would have to assign a certain qubit to each of the guys, and then you have to always swap the information. Because you cannot directly reach, for example, from 12 to 18. You first have to swap 12 to 15, 15 with 18, and then swap the information back. And this you have probably seen is a swap gate. Yeah? I don't go through the details of the swap gate. That's a basic looking at quantum computing gates. You can look it up. It's well documented everywhere. So for swapping the information of the quantum state, which is carried on 2 qubits. So here's the example. This is state psi. It's carried on the 2 qubits. And it consists of amplitudes for 0, 0, 0, 1, 1, 0, and 1, 1. And the swap gate changes the information regarding 0, 1, 1, 1, 0. So if the wave function in the beginning is with the coefficients alpha, beta, gamma, delta for those four basis states here, the outcome will be where gamma and beta have been switched. They don't need to switch alpha and delta since those correspond to both being in the same state anyway. But this consecutive usage of controlled NOT gates, so C-NOT gates, arrives at this result. So you need 3 C-NOT gates to swap the information of these two figures. Okay? So do you remember why I don't want to do that? Errors. C-NOT gate was the crucial error when you go to hardware. And if you need a lot of swapping because your problem does not fit the topology well, then you generate a lot of additional gates, and these are the noisy gates, so your algorithms will fail. Again, there's something you don't have to bother about if you simply do a state vector simulation, because then you have no noise. You can put hundreds of C-NOT gates. As soon as you put a little noise, swapping will kill you. So you cannot avoid it always, but we can try. Can we do better with the model than we have? So, this is the model. Purity, bath, hybridization. It looks like this. We want to get to that looks more like this. That we could put on the linear topology. We could put on the chip. So can we get from here to here? Okay. Question is, how can we do it? And the thing is, it's a bit more tricky than going from here to here. So why is that? What is missing in this picture? I want to find the transformation so that it works without losing, let's say, mathematics. But I use connections, so it's getting easier. So that's what I want to achieve. But I'm in this picture, I'm missing 4 regions. Introducing the next thing you have to care about. Here I go back. If you look at this picture, so what do I miss when I go from this picture to this picture?
I repeat your middle thing just as one level, right?
Right. This picture is just showing one level, and we have 2 levels. We have 2 electrons. We have spin up and spin down. So it's a bit more complicated. We have in here 2 levels. We have outside 2 levels. So inside they are split by the energy, the outside interaction, but it's all only on the correlated orbital. The others are not interacting, so they are degenerate. But we have these 2 guys everywhere. So actually what we want is not such a chain, but we want to have such a chain. Okay. Well, we can easily separate the left part of the chain as being spin up and the right part of the chain as being spin down. And because the only point where spin up and spin down talk to each other is here. Yeah. This is a sum over spin, so they're independent. This is a sum over spin independent. This is a sum of hopping reserve spins. And only here, there's 2, you call them spin sectors. So the 2 spin sectors are connected only via the interaction union. So I draw that as a double line. So this topology we want to achieve. So let's look how we can do it. So if we write who is coupled to who, now again I just draw one box, which always means I have the two spins, yeah, but we keep in mind we can decouple them later by, let's say, unfolding this chain to the left and the right part. And we put on the first element in the matrix, that's the correlated orbital. So the correlated orbital at 0 talks with it, or at 1 talks with itself. The correlated orbital talks to all the other bath orbitals via this coupling. So that's the orange box. And then there's also each bath side talking with itself. So that's the matrix we have. Look at what are the connections. Where do these operators with which other operator are there? There's a matrix where there's essentially everywhere 0, except for the top line, the first row, the first column, and the diagonal. So that is representing the connectivities we have in this model. And what we want, so how would the connectivity of such a thing look like? Try to derive what do we want? Let me write this. Then just to explain the matrix we have here, we have the correlated orbital. The correlated orbital is connected with itself. Yeah, that's this term. You can just think about spin up and spin down in one matrix. Otherwise, I can put it like a 2x2 matrix here, and there will be some elements here everywhere. And then this will be bath side 1, bath side 2, and so on. And these blocks will contain those VI terms. Then here there will be this epsilon I. Since I'm writing, that's it. Hard to see, but the block up here, if you would put that again as spin up, spin down, spin up, spin down, and there will be epsilon D, and spin up and down. Yeah, so you could write that as a matrix. That is depicted here, and it corresponds to the colors. So what do we want to have? I think this. It's hard to see, right? The pen is not perfect. And there was a.
Here's something.
Okay, so the orbital itself will be connected with itself. That's not a problem because that will be this part here. So this part of the matrix will stay the same. And then we have in the new numbering here, where we need, let's look at this one first. We have the chain. Yeah? So this one is coupled to only the first one. Okay, it's only coupled to the first one. There will be something here. And then there will be zeros. Because this guy is not coupled to this one, it's not to this, it's only to this next table. If we look at the next neighbor, this one, there will be the curve with itself, and then it's coupled to the impurity, so the correlated orbital, this is a bath 1, put a tilde because it's the new bath, bath 3, and so on. And so this will be covered to its next neighbor. And then there's zeros. The next one will also be covered to its next neighbor. And there's zeros. Yeah? So that's the form. Anyone know how to call such a matrix? Triangle, right? That has not only on the main diagonal, but the other two diagonals. For the triagonal matrix, there are clever algorithms how to get from one to the other. Yeah? So, for example, householder triagonalization. Okay, so we can use this algorithm. We can plug in the parameters here. So we plug in this matrix, we get the different matrix, and so I've been a bit. This was not completely correct because all these parameters now get a tilde. It's not the same parameters. Here they are because this part is not changed, but the others change, and that's why I changed the colors. So this transformation, you will get different couplings, but they all are along this chain now. And you will see in a minute why this is extremely useful. Okay, probably you will not work on the Anderson impurity model, but on some other models. But the message here is you can gain a lot, and I think Leonardo said something once in his talk. You gain a lot from looking at the topology of your chip and then assigning or trying to formulate your problem in such a way that it best fits the hardware that you want to solve. To avoid the number of gates being too large. Sometimes you can have, you're lucky and you can play these tricks, and this reduces the amount of swap gates because you do not need to switch always these informations to get to the others. But they're already in the line, and we can now look at this chain. And now we need to first, before we look at how to put this on the quantum computer, look how we assign its electronic orbitals, which are depicted here with qubits. And the natural way is to say, okay, each circle here corresponds to one electronic orbital, and this corresponds to one qubit. And then I say qubit in state 0 means orbital empty, qubit in state 1 orbital occupied. That's the most natural mapping between electronic states that can be either empty or occupied. So it has exactly two possibilities, and a qubit which has exactly two possibilities. You have a question? Please.
I have a question.
You have a question.
Yeah. So showed us this transformation from the original matrix to the triagonal matrix. And the question was, is that just a basis transformation? Is it just there kind of unitary that it's there? So it's the same information in the new level as in the
Yeah. But I think you cannot simply write down unitary transformation. So you go through this algorithm that subsequent iterative algorithm triagonalize the matrix. That's not a uniform matrix that you can just produce. Okay, so let's look. We have this state, the correlated orbital, we call it 0, and we count the bath states 1, 2, 3. So here we look at, let's say, the example of having 3 bath states with spin up and spin down. So again, we separate the spin sector. And we take 8 qubits, and we just say, okay, maybe qubit 1 is this one, qubit 2 is 3, 4, 5, 6. And each time the qubit is in state 0, the orbital is empty, and in state 1, the orbital. Then we look at our coupling map, our chip, and we take 8 qubits in a line. For example, those. And here's the next important thing. Is if you run on hardware, I go back, you see these different colors. I told you yesterday, they show you graphically. I took this from the user page. There it shows you the errors, the fidelity of the qubits, the error rates of the connection. So you see all these colors. So it depends which qubit you take. They are not the same. They have different frequencies that are addressed. It depends on where they are, let's say, in the material manufactured, if there's some physical defects close by or not. They're all individual objects. Yeah? Of course, manufacturers try to get them more and more uniform, because this is the problem. It would be much nice that every qubit reacts the same, has the same error. And you see the different colors, so I don't have the color scale here, but it can be that one is pretty bad and the next one is pretty good. I think this is the other way around. The darker the color, the better, and the more red it's bad. But you have to find a compromise. And if you look for 2 qubits, yeah, maybe let's just look at 2 qubits where the colors are dark. So you put 7, 10, or you can take 25, 26. But if you want to take 8 qubits, you must find a compromise. And it's a different optimization, very difficult optimization problem. You're pretty soon lost looking at it by your eyes. There are some companies that offer, there are some startup companies that offer some add-on packages that try to give you the best set of qubits, best way of addressing them, and so on. So people have thought a lot about it. But the problem is that also this can change. Yeah, that there's a calibration of the hardware running at least once a day, where they calibrate their frequencies, where they calibrate their gate operations, and so this is something which changes over time. That's important to be aware of. If I run an experiment on a set of qubits today, and tomorrow it will be different. It's even if I run it now and I run it in 1 hour, it can be different. And that's the stage we're in. It's noisy, intermediate scale quantum. That's the same, still true for every of these machines. That's because it's such a delicate thing. And you can, we monitored, we did a very simple job, and we ran it for 2 hours, and you can see how things are oscillating. Yeah? And so there's a lot of influences working on the chip. And then there's this what I named TLS, 2-level system. Suddenly appear. There are 2-level systems because they're called 2-level systems because they act like an additional qubit, an additional pin somewhere, but one which was not foreseen, which is somewhere in here, and which now starts when you couple and react and disturb. Something the IBM people told us after 1.5 years, that they have no idea how to get them away. You just have to wait. Sometimes they disappear, sometimes they move around in the chip, and it's not even clear what is the origin of that. But just be aware, these are problems when you try to do something on real time. Okay, now let's take those 8. And now the next thing, and now it's getting a bit of math, but straightforward math. Here we have the operator written in these second quantization, these operators of creation and annihilation operators. So you can think of it, a creation and annihilation operator means taking away a particle or putting one. And so I remind you, like we have this sequence here, if you have C dagger I and C I plus 1, yeah, means that on this state, and let's call this is state, let's go here, this is state I and this is I plus 1, yeah, so I is 6 and I plus 1 is 7. Then this means that I remove 1 from 7 and put 1 on 6. So that is the movement, yeah, that was the term from the coupling, from the hopping. There's always a C dagger with an I and a C with either one larger, or if you go on the other way, one down. So this one is the other way around. Yeah? It destroys one on the lower one and creates one on with the index one larger. And we said that these terms here, where you have the same, yeah, it's counting. Yeah, it's like taking it. Ah, there's one, and putting it back. That's counting. You can think of it like that. And now we need a transition of these operators into qubit operations. So what are qubit operations? What qubit operations you know? Qubit operations. Panama, yeah. One of the easiest ones, but the most basic ones. Oh. So it's perfect. It would be perfect if we could find a transition, a translation of these operators into Pauli's. Yeah? And so let us also know what is in Jordan-Wigner mapping. I write you the solution. It looks like this. We try to understand this. Some of you remember that Andreas Hugenberg and his work had also something, some sigma Pauli's, sigma plus Pauli, that also had this x minus iy, and maybe I put the other guy, which has the x plus y, and I'm missing an I here, sorry about that. Look at the Pauli's. So let's look at the last one first. So it's xi plus or minus, or let's put it the other way around, because there's minus on the top and plus on the bottom, I, y. Okay. So we can write this down with the Pauli matrices. Get here the I inside, so I times minus 1. I times I is minus 1. We get x minus iy is the difference. Okay. And then take the factor, that's factor 1/2, because we're there, it's 2 here. 1. And so that's everything without the z. I talk about the z in a second. So we get these things. So we can see that if I have a state which is 1, 0, and I apply this operator, this will go to 0, 1. And here will to the 0, 1 will go 0 with this operator. Yeah? Meaning that if I assign 1, 0 to be the 0 state, then this one generates the particle because afterwards it's the 1 state. Yeah? And if the other way around, if I start with 1 state, it will be the 0, this will be 1. So this is exactly what it should do. Yeah? It should generate a particle or erase the particle. Putting the state 0 to 1 or 1 to 0. If you put the other way around, so if you start here with 0, 1, this will just be 0. And if you start here with 1, 0, this will just be 0. So it has no action. If it's already empty, I cannot take anything else than 0. Sorry about my handwriting going down. But that's the always when you have these combinations of x, Pauli x plus minus I Pauli y, that's always connected with creation and annihilation. So why are there so many Z here? So this is a product, yeah. So product of Z Paulis acting on qubits 1, 2, I minus 1. So this is the definition for creating or annihilation a particle in orbital I. And I have Z Paulis for all orbitals smaller than I. Any idea of why this is? Anyone has seen that or thought about it? This is really a pain because there's a lot of Pauli Z, which actually I would not like. Which causes a lot of trouble. So it has to do, one hint, it has to do that we are looking at electrons. And electrons are fermions. It has to do with electrons and fermions and the position where they are in the numbering. Okay. So if I remove an electron from one side and put it somewhere else on the other side, you will remember something, or those who had quantum mechanics, what you have to care for if you have many electron waveforms. No? So there's a basic principle in quantum mechanics that fermionic wave functions need to be antisymmetric. That means if I change the position of two electrons in the wave function, so if I would have a product of I and I plus 1, I have a product of single particle orbitals. Yeah? And if I change this order, so that a different name, so that electron I plus 1 is now an orbital psi, and electron I is in the other one, I get a minus sign. And this antisymmetry of the wave function is ensured by having all these sets. It's the only way of keeping this basic principle when you calculate and work with fermions. So we always have to carry this in our calculation. Now, one word, you have a set of Pauli operators here acting on different qubits. Yeah? We had selected some qubits, and so each Pauli acts on the qubit with the index. Yeah? So those Paulis I can change because it acts on different qubits. So it doesn't matter. Yeah? I could put this sum on the other side, yeah? Since they are all not I. Yeah? But I cannot exchange the order of Paulis with the same index. Yeah? If I have a product. Yeah? That So having this rule, let's try to calculate what we need here. So let's start with this guy here, which is the number operator on orbital I. And we put these two expressions. So we plug that in, and we get this. As said, since I can change, I can move around Pauli's with different index, so acting on different qubits, I can collect the sum of the Pauli Z from this guy and the sum of the product of the Pauli Z of this guy and of this guy. You just can collect them at the end. So I have the xi minus iyi and xi plus iyi. And I have a product, and now I have the square of Pauli Z because I have one coming from this and one coming from that. The square of the Pauli matrix is what? 1. So luckily I can take that away. If it's 1, I'm left with this, where now I cannot change the order. So when I change the order, I get a minus sign, but this is good here because then this middle term goes away. I'm ending with as not going away, it's giving you the so you can simply put the matrices. I always have to look it up. But this is just calculating with those matrices, and you end up with this expression. So we boil it down, all these Pauli operators at the end to be a single Pauli Z operation and some constant here. Okay, let's look at what happens when I have Ci dagger and Cj. So two different indices here. Now the sum at the end will not be for all the z's, because in one term I have it running until I minus 1.
One will not work because I have to move. So maybe just for the second, but otherwise I'm too much blocked here. So if we write that down, we have one sum of and let's say now j is larger than I. So I have one sum here coming from the Ci dagger, and the other sum coming from the Cj. And so some of the Pauli Z I have twice, while if j is larger than I have some which are only once there. And so again, for those which are paired twice, I can erase them because they're equal to 1. But I cannot erase all. I'm left with all the Pauli Z which are in between I and j.
I write that down, and now take that term and the one with I and j interchange. I end up exactly with 2 terms. So I leave the dots for you. Do the calculations. It would take too long now. We want to get to the quantum computing result. But in the end, you will be left only with the terms with this x, and and it's the Pauli Z in between, and this y, and this y, and the Pauli Z. The other terms cancel. That is nice now, because since in our chain topology we only look at next neighbor. And so I is all the I in J, so J is always I plus one or I minus one. So there will be no Pauli Z index. It's only XX and YY. But these are these two qubit gates, yeah? So acting on X on qubit I and I plus one, but neighboring ones, which we can implement. Okay, before we take the next step, is there a question regarding this mapping and how to do the calculation in principle? You should write it down on paper and looking at the commutation and anti-commutation relation of the Paulis to verify that it is true. Good exercise, but other questions were. This is in general. Yeah, this is in general. And here in this sum, because we have this topology, it's only I and I plus one. Okay. So, but if you would not have, if you had a different model, you have to take care about all these Z. Only because in our case, J is just I plus one or I minus one. Yeah. We have the question.
Comment. There's a half over there. No, in the end, so much worse was a half and then plus then a half comes because there is a tool. It's a 2IZ. That is correct. Romance.
Yeah, one can easily mix this up, so it's important to do it in a quiet hour on a sheet of paper, not forward. But you get the principle, okay? Right, so here's our chain topology, our qubits. Now, if we want to do that on a quantum computer, it's still too much. Yeah? But okay, let's summarize what we learned before. So we learned that the number operator is Pauli Z. So we can translate this part. It has number operator. It's two number operators. So we can translate that in one term where there's individual Pauli Zs acting on individual qubits, central ones, and one term where there's a ZZ gate. Two qubit ZZ gate represents the interaction between spin orbitals on the quantum photons. So, like this, we can write down this part of the Hamilton. Only involves Z gates and a ZZ two qubit gate. So, similar argument applies for the Bass sites. It's also number operator for Bass sites. Now we get Pauli Z of Bass sites. So these terms are very easily implemented. Finally, the last step is we have to look at this coupling or popping or tunneling or whatever you call it terms, which involves XX and YY gates. And this translates easily to XX. So that's the Hamiltonian written in Pauli's. And now it's not quite correct up to now. Who notices what's missing? Look closely at the arrows, look at the result, and tell me what's missing. Nobody worried? I plug this, and this into the upper equation, I don't get the lower equation. It's just part of it.
Come on, one must be awake. Okay, one hint. If I take this, I plug in this would be exactly that, okay? Because these operands are exactly written up here. Okay, here's D. That's why I use it with the D's. Never mind, but this is exactly this. But here and here, I'm missing something. Dagger D. Put D, dagger D. 1/2 over I plus this. I get this. This, this. Where's this? Okay, the first thing to notice, there's no 1/2 here. Yeah? That's simply because typically one doesn't write the 1/2 and just renormalize the parameter. Okay, so I didn't put it here. I should put 1/2, and then you call 1/2 epsilon I instead of u epsilon I. I want to carry around this 1/2. But this is identity matrix missing here. I don't put it here, and I don't put it here. Why? Why can I leave it away? If I there's a function say that with the identity, yeah, nothing important, just at the end the constant, the shift. Okay. All the identities that appear here, they can, if you will do the exact calculation, you can collect all the terms where there's no Pauli at the end, and it's just a constant. Now, important lesson learned. If you have a problem, quantum chemistry, solid state physics, whatsoever, and you find a certain good translation to Pauli's, check what this term is. Okay. If this is very, very large, and this can be very, very large, because you could choose a very clever topology, you can choose a very clever set of orbitals, then this can be large. And this can be small. And you will end up in a problem that you actually more or less have solved already, because the solution will be that, and there's some small correction to it. And the quantum computer can do whatever it wants. The solution will be good because you have a very good start. Several papers out there are exactly that way. Yeah? I say it's like putting a golf ball close to the hole and just do it like that. They don't say something wrong. It's all correct.
But they have found a clever basis, they have found a clever subset, a clever topology, so doesn't care what the Pauli sets are. Right? And so, for example, the paper with the first hydrogen molecule, they use Hartree Fock bases and so on. Yeah? So you will find out that this value is like 0.9 or something, and the rest will be 0.01, whatever. But that's really important. It's not important. Just a word of caution. So it's on one hand, it's important to see how good you are already before you do any quantum computation, but afterwards we can just add it at the end. Okay. So before we take a short break, notice this is still too complicated. Since the first things we did on the system, we still had lots of noise. Now we're at more larger system. So let's first look at whether this works in principle. So the smallest system we can look at, the smallest proof of principle system is just one orbital with spin up and down. That's a correlated orbital and just one orbital and down. That's the minimal model you can think of. It's called the two-side Anderson impurity model. And that's now our playground for running computations on the quantum. It's again subsequently building up understanding. If this model works, we can put 2 bath sides, 3, we can 4. And if this model works with, let's say, 20 bath sides, we can start with the second correlated orbital, and so work our way through. Don't start with the most complicated version. So, Hamiltonian will be much easier, since now it's only a 0 and a 1 qubit here. So qubit numbered by 0 and 1. And so you will have the first term still, as always, is the quantum impurity with a on-site interaction U. And you have bath state and spin up and down, and you have these terms x, y, just between light blue and the green. So, how to solve this proof of principle model? Any ideas? What can be done? I give you a hint. You can use classical or quantum approaches. Let's start classically. How can you solve such a model? Mathematicians start to solve this model. Okay, then I don't know which physicist said that often. I say it was Feynman, but don't care whether it was Feynman or not. It was shut up and calculate. Sit down and calculate. You can simply calculate it. Simplest, very simple. There's an analytical solution. Maybe it's not that simple if you never worked in this formalism, but there's an analytical solution. If you cannot do it analytically, yeah? How big is the matrix connected with that? So we drew the matrix before, yeah? So how big is this matrix now? Okay, there's 2 options. There's one which you could think of, which is wrong, and one is right. So there's 2 options. Anyone guess? 4 by 4. It's a 4 by 4 matrix. You can write it down. You can diagonalize. So a 4x4 matrix you cannot diagonalize easily analytically anymore, so then the solution is not diagonalization. But you can write down the 4x4 matrix as similar as I did before and do what is called numerical exact diagonalization. Yeah. Plug it into your favorite mathematical code, MATLAB, Origin, whatever. Yeah. Octave, I mean, whatever. It works, it's easy. This does not work when you have 20 fast drives. Then you have n to the 20. As a big matrix. So things will slow down, will get problems with memory. But for 2, 3, 4 bath size, it's no problem to solve it numerically. And the good thing is, for the small model, there's an analytical solution. So we can compare everything, every calculation that we do, we can compare it with the exact one. It's always good to know. And so quantum, what can we do on the quantum side? Well, I'll show you the quantum variation algorithm. That was our first guess. And the second approach is Hamiltonian time evolution. And well, there are several other ideas that we are and other groups are working on.
And with that said, let's have a short 10-minute break, and then I show you the results of the hardware. And if you have questions in the break, please come. I'm here. I'm happy to help you. So let's start at in 10 minutes again, so 17 past. Wenn du das Ganze mal zappst, kommt irgendwer raus, dann ist das ein Schulmodell, Rabattmodell,
Wann stoppen? Ja, aber kannst du Prinzip nicht schon auf? Man schon zeigen.
threshold is Setzungszahl auf so ein bisschen genau Eins, zwei, drei, vier, fünf, sechs, sieben, acht, neun, ja. Dann reicht noch. Dann abschließend weniger. Dann nächstes Beginn und da war jetzt Banane. Ja. Of those is also here. That included that. before. They determine really molecular. So well, idea. You have this one thing. And here the process. That's not the object. And often interpreted as if they are, they're not. If they are molecular, the big correlation is important, it's not the same. Our objects do not have the meaning of what it is. That is why EFT good. Well, after a talk, it's a look at orbits. Once you say that doesn't work. That idea of real multi-particle correlated wave function. So data determinant would mean you have individual orbits of the same. But if it's not individual, you cannot find them. That's why I need it. Okay, so I think we can continue in a minute. Just before lunch. So the first approach to solve this proof principle model of 4 qubits is the variation of quantum algorithm approach. I showed you this slide yesterday summarizing the steps. So we have defined the Hamiltonian a few slides ago. We have found the mapping between electron states and qubits. Now we need to find a parameterized quantum circuit as an ansatz and to evaluate expectation values to find, for example, ground state. And I showed you that if you do this, please do not start with the hardware, but start with a hierarchy of simulators and backends. Start with a linear algebra calculation, whether it works at all. Then look at what is the effect of stochastic noise, probabilistic, using a probabilistic simulator. Still without any gate or device errors. Then look at a noise model, including gate errors and coherence times. And then, if you want, you can go on the hardware. I show you that convergence is very different in the regimes. You need different optimizers to converge your variational algorithm. Sometimes it does not converge at all. If you think about what to do with this noisy data, where you get the result to continue. And nevertheless, we took all those 4 steps and went through on the hardware. So let's start with our VQE results for the ground state of our 2-side energy impurity model. And with so that's on the left, I'll explain what you see here in a second. And the second state, which is an excited state. Yeah? So remember, we were calling this a half-filled state. Certain conditions for the parameters were half-filled. Then putting an additional electron on the electron state while removing an electron would be a whole state. So what you see here is the expectation value of the energy of the ground state, and here of the excited state. And it's been given in units of T. So T was the hopping, and it defines the energy scale. And you see dashed lines that are the exact values. I said that the model is solved, can be solved analytically, so we know what we want to have. So we want to have the dashed line down here. And we did calculations running VQE for different number of shots, 500, 1000, 5000, 10,000. And you see all the dots are individual VQE results. And so this down here is the circuit we employed for the ground state. It involves this A gate. The A gate, I don't spell it out, it has 3 CNOT gates. So if we have these 6 A gates, means 18 CNOT gates. The electron state is shorter. Here the ansatz circuit, it just has 3 CNOT gates. So what you observe, first of all, is that there's a large fluctuation of results. That is also yesterday when we looked at zero noise extrapolation, you've seen that you get sometimes really very bad outliers, huh? So you always need to do statistics. So these are 10 runs for each setting, and the red line gives you the average value of these 10 runs. And what you see is that when you increase the number of shots here, well, it's pretty bad throughout. Huh? You are more than 10% off the exact value. And this bothered me a long time. We tried a lot to get better than 10%. Looking at the paper of IBM with the hydrogen molecule, also 4 qubit, where they claim to have such good results. And this is exactly what I mentioned before about epsilon 0. In our case, epsilon 0 is small. So all this is a quantum computer. The other case, what we focus is the main solution, and the quantum computer does a bit of wiggling. Because, for the excited state, it's much better, yeah? It gets results below 5%, it's much better. Why is that? Okay, there's only 3 CNOT gates. Here's 8. So, you see how the CNOT gates destroy your result. So, this looks not very promising here. But now there's we thought, okay, can it be really that bad? I mean, not so many parameters. I mean, you can get with some of these, because of symmetry, some of these angles are 0 anyway, so it's not so many parameters to optimize. And we checked, I take the parameters and put them in the circuit, and put that circuit with the parameters that are obtained here, and put that on a state vector simulator. And then the result looks like this. So suddenly the results are all, well, the average values are much closer, and the values for the exact states even are almost exact. So what I conclude from that is that the parameters with VQE on the noisy hardware found the optimum. But the calculation of the expectation value that follows is problematic. And you remember maybe on that slide before, how do yesterday were all the open questions around VQE. One thing is how to efficiently calculate the expectation value without running into this problem. This is within the methodology of writing the Hamiltonian as a set of Pauli strings and measuring each Pauli string on the hardware, then summing up a large set of numbers, which all have a small error, but if that small error is systematically pointing in one direction, and you sum up many terms with a small error, you have a big error. So this is now, because I mean, we have 18 CNOT gates, it was not expected that the errors are so large. This is now understandable for these CNOT gates, and you see that for 3 CNOT gates, if you have enough shots, you get good results. However, even here, there's an outlier. You always need to do statistics. You always need to take a large number of shots. In other words, of course, you would say, if I only check for 500 and 1,000 shots, you say, great, 1,000 shots, I get the exact value. Yeah? But you see that the convergence, increasing the number of shots, convergence to that value. So in principle, the more shots you do, the better you should see. Yeah? More shots, better statistics. And it can be due to the errors that at some point you get the right result for the wrong reason. Yeah? There's different errors during the both. And if you do not do a systematic analysis, you think, oh, it's the right result. And I just look at the number and it looks good. But it's a cancellation of or different errors, one going in one direction, one in the other. And as soon as you try to do another problem, you're completely wrong. So don't be mistaken by these things. If you have like something which works with 100 or 500 shots, usually it's by coincidence. And we will later on, we will always compute with 10,000 shots. Otherwise, the whole algorithm does not compute. So things will be better on today's hardware. But we are not able to redo the calculation. Each data point here took several hours. It's impossible to pay for that. It was just at that time we had the access to the quantum and we could do it. I would like to see how that looks on a Huron chip. I can't pay for it. That's the problem of V2E. It's expensive in terms of how many iterations you need to do, how many shots you need to do. So as long as you have to pay for your computing resources, not a good approach. I'll show you a better one in a second. And this is because, essentially, because of that. Of that noisy optimization, you have to run a lot of time. In that case, if you do many shots and you can find an optimized between the number of shots and so on, but it will be expensive. Okay, so now we calculated from those, we did many eigenenergies and we calculated the Green's function. So remember yesterday, there was this relation between the Green's function and the spectral function. In the end, which is here that I'm not always taking the wrong. We're looking at the retarded Green's function, so the propagator, the response function of the system, and there was a connection with the imaginary part. I hope I get the minus sign correct. I don't know, but if we want to look at the spectral function, telling us how the system reacts with its environment, we need the Green's function. And for the Green's function, we had yesterday written something like epsilon, something like that. And so, which gives some peaks, and so you can imagine now if it's getting more complicated, and you have all this stuff. So you will get some divergences, some peaks, and this is exactly what you see here. Yeah? So this is the Green's function, exact diagonalization, the exact result. Yeah? Shows 4 peaks at 2 different frequencies. So one is more or less representing the dot, the interacting one, the other one, the other frequency or set of peaks comes from the fact that it's coupled to the bath state. So we have 2 frequencies at the dashed lines, plus omega 1, minus omega 1, plus omega 2, minus omega 2. Okay. And now if we take our results from the quantum computer, 1,000 shots with 10,000 shots, we take the red and the blue curve. Okay. So why are they not at the dashed lines? Yeah, the answer is always the same. Why are they not at the dashed line? Error. That's exactly the energies have an error. You've seen it was 5% roughly, yeah. Maybe more, so energies are wrong. energy in the denominator, saying where this thing has its divergence, if the energy is wrong, the position. Okay, here's some noisy feature, don't know why. You see, okay, 10,000 shots getting better, yeah, moves closer here, but still not there. And then also I showed you for even with 10,000 you have an error, so just simply increasing doesn't help. Okay, now the thing was that we wanted to go for the self-energy. I remind you, so coupling between those states actually gave a function which we call sigma omega, which is self-energy. And that's actually what is in this EMFT loop. So, and then for calculating the sigma, I mean, if you have an object without the coupling, and also which is a 0, and one with the coupling, you invert it and you subtract them, and that's sigma. No? If I plot sigma, this looks pretty bad now. So sigma has just two poles and 2 frequencies. That's the exact solution. That's the quantum solution. So that's now extracted from the Green's function. Yeah? So the Green's function looks like this. Sigma looks like that. Now the problem here in the middle arises purely because sigma is calculated as a difference of 2 objects. 2 objects, each having divergences, and each divergence is having some noise. So if you write it down, or you can do the calculation with a state vector simulator, everything is nice. And you would have, like I said, 2 divergences cancel each other exactly. Yeah? So mathematically they cancel, but as soon as there's noise, divergences don't cancel, and you get something here in the middle which disturbs you. Yeah? You want to think about this is exactly the point which we are interested in to determine the derivative here, and then so this is the one where things are get messed up most. You have to think about how to go on with that. And but the one thing I wanted to show you is now, okay, I rerun the computation, and we did several runs again on IBM Eningen, 10,000 shots, so once, the second time, the third time. You see the results vary. Yeah? Sometimes you can get pretty good results, sometimes it's really awful. So the left is the Green's function, on right, the self-energy. And now, yesterday I told you about zero noise extrapolation, inverted circuit zero noise. So if we do the inverted circuit zero noise extrapolation, you see that in general it gets better. Here, much closer, it's really nice. The zero noise, the inverted zero noise works pretty well in general. So when you are already quite good, it gives you better results. But if you are pretty bad, yeah, it doesn't help. So like say the third run is really far off. Okay. So that's the status of the VQE calculation on this model. And I stop for a second if there's a question of VQE. If not, then let's look at the next second possibility, which is the time evolution. For the time evolution, I can try directly to measure the Green's function. And now the set auxiliary should be the retarded Green's function. And you can write down how this Green's function should look like. So I spare you the mathematics. If we have another lecture, we could go through it. It's again substituting operators by their representation and the short linear transformation, and doing the same thing as before. And you come up with expectation values to measure with x and Pauli y. And the idea of how to do that is to use a Hadamard test like procedure. So if you want to measure the expectation value, this kind of operator, how can you do it? Well, it involves Pauli operators at different times. Yeah, we were talking about the Green's function tells you something about I disturb the system at one time, and I want to find out how is the response of this perturbation at a given time in a later time. So there's some time in between. That's what one calls propagation or time evolution. So the Green's function is time dependent, and it's for larger than zero. That's the retarded. That is a mistake. Should be retarded Green's function. And so it involves a Pauli measured at a certain time, zero here at the time, later time t. So what do? We prepare the system first in the ground state, since that's where we start from, the ground state sign on. And we do a Hadamard on an auxiliary, an additional qubit, we do a Hadamard. So the state we of this system at that point will be in the state which follows the Hadamard, and the other register will be in the sign-on state. The next step is to do a controlled Pauli operation. Yeah? Controlled Pauli operation means it only applies if the control qubit, which is the upper one, is in state one. Here we let it controlled by the state zero. So if it wasn't zero, then the Pauli matrix operates, and if it's not, it does not operate. Okay, that's why there's the white dot. So controlled by zero. So the state will be the superposition of that. It's a superposition because we start from the superposition of the auxiliary qubit, the Hadamard gate. And then in that first case, we have the Pauli second. Then we have to implement the time evolution. So we want to implement the effect of time. So we somehow have an operator expression for that. I come to that in the next slide. So that will act on our side of the time evolution. Then we do another control operation, another sigma operation, now controlled by the qubit being at 1. So we end up with this object. This is the wave function here. And then we do another Hadamard of the first one. Okay, so then again the 0 state goes into 0, 1 over superposition, and the 1 state goes into 0, 1 superposition. And you can write down this. Okay. So we have prepared the whole system in a complicated superposition of terms here. And we have two Paulis in there, sigma with alpha and beta. And now depending on which term we want to calculate, so we take the first Pauli to be x, the second to be y, or the other way around. And then how to determine the function? We then have to finally to measure only the auxiliary qubit. And we measure it in a z basis, then it's the real part, and so we measure it in the y basis, it's the measure. And again, I would like to go through this. It would have really a full week of lecture. I don't have the time, so if you like, you can try to figure out this. And if it's too complicated, you can look at Wikipedia entries of Hadamard test. So Hadamard test in general is not for this Green's function, but it's similar. You can get the idea. Yeah? And do this as an exercise. Why the measurement in the Z basis gives you the real part, and why the imaginary part of, let's say, this object if both Paulis are X. But it's a direct recipe of how to measure directly the Green's function. Before with the VQE, the approach was I measure excited states, I measure ground states, I make a construction similar to this. I didn't show you all the details, but I express the Green's function in terms of ground state, excited states, overlap matrix elements of this. Here I directly measure it. You don't need anything variation. So time evolution operator. The time evolution operator is the exponential of the Hamiltonian. In the Hamiltonian, with this qubit mapping, we wrote in a series of Pauli. Yeah? So there was Pauli X, Pauli Y, Pauli Z term. Now the bad thing is that the Paulis do not commute. Yeah? So when I want to, let's say, I mean, I don't know how to implement the exponential on the quantum computer, but maybe I can go forward by implementing or finding an approximation for a very short time step and repeating that short time step many times. And so the idea is, instead of having one unitary time evolution for full time, take several small time steps. And this is called a trotterization. Put forward from a guy named Trotter. And there's further approximations how to deal with this non-commuting Pauli strings, which is called Lead Trotter or Suzuki Trotter approximation. Never mind, now it's just you have to be a bit careful when writing an exponential as a product of exponential if you have a term non-commute. But the idea is I have a circuit, a ground state, I change individual Trotter steps. Each are now a circuit that I can evaluate, and I can measure, and then agree to. So, back to our Hamiltonian. This was the correlated orbital in second quantization and in Pauli. The bath in second quantization and in Pauli, and the coupling in second quantization and Pauli, and this is the constant energy. And I can directly translate each of the terms gates. So here I have Z gate and Z gate, and here I have Z gates. So these are the first four Paulis, yeah? And depending on the value here, I have different rotation angles. So the first four single qubit Z rotations are this energy and this. And then I have the one-side interaction U, which has a ZZ, it's a 2 qubit gate, a ZZ gate. And it connects our central atom. And I also put on this slide the color because I think a different set of slides that we did stuff. I will buy those slides with all the others on, for you. I will update it. Then there will be this interaction, it's exactly this ZZ gate. And then I have the coupling hybridization circuit. 2 XX gates and 2 YY gates. So these are these gates. So having the Hamiltonian for a small time step is of this form. And because we have the linear topology, if we now go to a larger model and we have several spin up or spin down states, this we can build it like for a brick wall structure. So you can evaluate those gates at the same time. It doesn't make the circuit much longer. You can evaluate gates acting on different qubits at the same time. So that will be the form of the circuit that we can now evaluate. Before we do that, we look at the shot noise. As I told you, let's go through the step by step cast simulator. And we choose just the step width of the time, 1 quarter here, 10 shots, some here, while you already see some of the major features are already there at 10 shots. But that's because we take many steps, and we look at an oscillating function, that we do the Fourier transform, we recover most of the peaks. In this area, the peaks in the imaginary part is that the peaks in the spectrum function, while the real part should be 0 and it's just noisy. And we continue with 100, 1,000, or 10,000 shots. And okay, you see what we want to see, it's getting better and better if you go from top to bottom. So with 100 shots, the features are well reproduced, and we repeat, it's getting better for And if we now take a noisy simulation with 0.1% CNOT error, well, okay, we need to go a bit larger number of shots, but we see the results. But the point is, for the simulation, here we could go to large times, and you see that there's no decoherence. The other noisy simulation just assumes CNOT error. We can get this oscillations of the Green's function to large times. That means we get a high frequency resolution. We could get good peaks here. Now, what is happening when I look on the quantum computer? So these are now results from the Aachen system, which is here on R2. So when we compare, this is again the exact quantization result, and we calculate that on the hardware with 1,000 shots. Okay, we can measure the Green's function. So this is a lot of data points. This is 1 quarter. So I have made one quantum circuit for 1 quarter, and so 20, it's then 80 circuits, and so on. Yeah. So I run each time individually, and then collect all the data points. You see, the longer the times, the more Trotter blocks I need, the more CNOT gates I have, the larger is the error. That goes down to 600. So you see the major oscillations, yeah, but they start to get out of phase here. You can see, okay, it's not visible in the back, the light gray. So each run, of course, is again individually, and you have statistics that you have to repeat. But that's what you would get out of the state-of-the-art quantum device, the time evolution. And the typical error rate here is 0.1% of the signal gate. So one thing is that that the machines have different implementations of CNOT gates, of gates. They have different gate sets. So we can also use RZZ gates directly. Then you have less 2-qubit gates, because you can decompose each RZZ gates in simple in 2 CNOT gates. So if you can directly make use of RZZ gates, then you can go further in time. Yes, so the result is much better. It's decay, but it's much better visible than oscillation. So it's preferable in this case to use the RZZ gates. So whenever you have different possibilities of the hardware, you can check out which one gives you the best result. Next step was we were talking about error mitigation, M3 error mitigation. So let's put M3 error mitigation, and we actually rather see the big effect. Yesterday, I showed you that the error of the old hardware was around 3%. The measurement error of the new hardware is below 1%, 0.5%, and that doesn't mean with all the other errors that is not available. So you can use it, but it makes no difference. Then we applied a filter. You have the circuit, you measure the ancillary qubit, you can also measure the rest. You can measure the whole register and look, does it have the correct symmetry? If it does not have the correct symmetry, you just drop the run. You just drop the shot. That means, okay, the longer you run, the more errors you have, and the data set reduces. Yeah? So for the long time scale, 70% of all my runs don't have the correct symmetry anymore. So I can throw them away and just not care. So yeah, it gets a bit better, you see. After the filtering, the oscillations can be seen a bit longer. But overall, the problem remains that your oscillations decay, and so it's not possible to measure this approach long enough time scale to really recover the Green solution. In principle, it's a good approach because each of these runs just takes 3 fractions of a second. So you can take such a curve on the order of minutes, not on the order of hours. Yeah? So you can Then depends on how often you have to do that to get it consistent. And then dynamical decoupling and switch. Then maybe the ZNE. So again, then you can look at which type of fitting to the data do I do. It gets always a bit better, yeah, but not, it's not a revolution. And you have to do a lot more calculations for the ZNE. So it's getting a bit better. We can get so, especially the green line here with linear fit is promising. And then for the inverted circuits that even overshoots. Yeah? I showed you that yesterday the inverted circuit ZNE that overshoots the result. So there again, I don't know whether it's trustworthy. But that's how far you can get on the current hardware if you try to do these direct simulations. But as soon as we approach the regime where the noise is much lower, or you get even error corrected qubits, then this direct time evolution is a nice approach, yeah? Because you can directly map your Hamiltonian onto a circuit. You can repeat it for different time steps. You can sample the function you want, and that's why it's called Hamiltonian time evolution. You use a Hamilton operator, and you really measure the function as function of t. And yeah, we continue to work on that. But that's all I wanted to show you on the hardware results. Now we're about close to lunchtime. So are there questions right now on the hardware results, on the time evolution? Is everyone hungry? Okay, I can understand if everyone is hungry, me too. So let's close it here. And if you want, I'm staying here, and you can also come if you have a question, or we can look at some of the other slides together if you want. Or during lunchtime or afterwards, I'll be around. So thank you very much. Sowas, ja. Oder ungefähr, ja, das ist so mein Ding. Nimmst aus, was statt, also ich denke, so, weil immer irgendwie solche Dinge. Aber weiß nicht.
Please, can you pay attention here? There is a form inside your Zoom, okay, and then you are supposed to fill it, everyone. So please, if you not fill it, please do it, okay? Thank you. Yeah, if you've already filled it, it's okay. Hello. Sorry, for the students, their lunch delayed a little bit, so you have to wait a little. Okay, we'll come and call you back.
Where's that?
Yes.
Like, first of all, the lecturer had an issue with his handwriting. And it's with variables, check the handwriting. What is the handwriting? It's never gets it. It's empathy, you don't get it. It's expensive. How can the lecturer charge?
Highly respected. It is with immense pleasure that I want to tell you. Yeah.
Exactly. Yeah.
I think here, I think this place I also can. Yeah, two that two, two, three, and after then get back there. Fox, I don't know if the thing that we are so, I think I have. Yeah, I have here. But they didn't have it, so, yeah, we, and in a way, so much was. Yeah, like, oh, it's more purpose.
Yeah,
My,
Okay, are you ready?
So we start this section. So what we'll do today is that we will together explore
the IBM resources that are available to everyone. Okay, this is a colored version of Mr. Qubit that you know. And this is what we are going to do today.
So first, there will be you have to create a free personal account on the IBM platform. Who has already an account on the IBM platform? Can you? A little bit higher. Okay. 1, 2, 3, 4. Who has already used the IBM platform? You have the account and you have this. Okay. So this tutorial will be for maybe who already has done something, we can someone anticipate some notebook.
You can give a notebook.
Because otherwise you just start from the beginning. Okay. So we will explore a bit so first what we want to do today is to use a composer, which is a digital composer for building parts of circuit and operating them. So you can really see the circuit as they are drawn to the particles. Okay. You can move, you can play, you can track the result. It's very intuitive. I mean, not completely intuitive, but then the second step, there are Python notebooks that can do exactly the same, but of course much more powerful because you don't have to click, drag and drop. I mean, it's like drag and drop programming versus real programming. Okay, then we can explore the IBM Quantum Composer. We start with the 1 qubit Hadamard. Then we will create a best state. We will create a multi-qubit Hadamard and see the state of uniform superposition. And then the task for today would be to create the state you like and to teleport it. Since you know how the application is working, now you can teleport in this quantum. And from one qubit to the other. Just creating again the circuit that we have done the first day, second day, first day. Second. Okay. So we'll be very interactive. I mean, it's nothing to show. I mean, we can show some stuff. We basically will follow you in doing this and playing and so on. Okay. So first thing, create for free a personal account on. You have just to search IBM Quantum on Google. Of course, you have to switch on the computer if it's not switched on. Everyone has to do it. The second one, platform. Then you have to say you have to.
So
you
you can go to
So you can also say with Google, with something, or Google, or the name. So you can prepare how to sign in. And
You can also sign in. From the laptop. But why this is shown, yeah, this should be shared, right? It should be shared. On the keyboard. Okay, so I go to IBM Contact I sign in. I was already registered. I guess with Google.
I create lights to name these computers the name of city. We are honored now. You have two cities of Morocco, IBM Fez and IBM Marrakesh, and one city from Italy, IBM Torino. And this is just the name of the computer. Okay. But you can't do very bad. The thing is that many of them with the Gmail name, dots everywhere, but they finish always in the same account. So you can just play with dots and have several free accounts if they don't track that they are the same. Someone has already done, and after a while, the brand is fine. Here you can see all of them. Boston, Kingston, Aachen, Pittsburgh, Brussels, Strasbourg. Ah, we have also Strasbourg and Miami.
And here you can see the pending jobs. So
And this is okay. This
the
is
less the number of jobs.
yes. Yeah. So this is the number of qubits. So IBM now changed the strategy. Is giving for free pretty good computers. Before it was not like that. And 5 years ago there were 5 qubit computers, 7 qubit computers. They were pretty noisy. Now it's getting much better. So there are these computers that are online. One is even in Europe, but the one in Europe is in maintenance. And this is the number of pending jobs. Do you know how it's working in high performance computers? Who knows? Yeah.
So if you have a high performance computer, you can imagine you have all these computers, much more powerful in a cluster, and then the users see all these computers as a unique, just to, I want to run on 4 CPUs, I need CUDA, I need whatever, and there is a satellite systems which is taking the job and is distributed in a smart way, knowing that the job find the resources, and there is, I mean, no conflict between jobs. Of course, if you are launching the same job on the same machine, on the same classical machine, that would be an overload for everyone. Quantum computer cannot do anything in parallel, sequence, but anyway, there is a number of jobs, so it is pretty easy. IBM Market is free, 0 pending jobs, and online. So maybe we might have chance to run also on the real hardware. And let's hope so. Okay, and there is another so pending jobs, number of qubits, they are all the same. This is another new stuff. And what is this one?
2-qubit error.
Sorry?
2-qubit error.
Yeah. No, I don't medium layer in the words. Okay. Okay, this is the average 2-qubit error order of magnitude. So 2 to the minus 3. Not so, I mean, not so bad. 2 to the minus 3 means 99.8% of error of fidelity, which is pretty good. Of course, this is just a number. I don't know how this number is calculated, but of course there are many parameters. You have seen there is the result error, this is just a 2-qubit error.
2-qubit gate error.
Gate error. Okay. So if you do a CNOT, you have such an error here. Every time you're doing a CNOT, 2 out of 1,000 of gate application fails. It's not failing, but it's giving something else. Okay, but let's explore. So if you want, you can create API key. Or otherwise, you can create later.
Yeah, let's go computer.
Maybe let's go to the composer. Yes. Where is the composer? Composer. Here on the left. Okay, so this is the composer. This is the composer. How the composer is. Okay, you see, I don't know if you see, but you will see on your composer. Here you have 2 lines. That means this is the classical register. This is a bit. This only will include the measurements. And these are 4 qubits, numbers from 0 to 3. Okay. Then you have on the right the 2 different way of writing the same circuit in languages. The first language is OpenCASM. It's an internal language of IBM. And the second language is Qiskit, which is a Python library of IBM. So as soon as you write your circuit on the left, it will appear here. Okay. So let's go to on the Cosmos side. Okay, so for instance, they have qubit registers, 4, and also 4 classical registers. But the classical registers are all put in the same line because there is many space for. This is a bit confusing. So here actually is not 1 bit, but it's 4 bits. And then you can play, like for instance, I would remove now some register. Okay, let's remove the register. And maybe we can start with the Hadamard gate. Okay, so you see on the right, Hadamard applied to qubit 0. One quantum register, 4 classical register, Hadamard applied to qubit 0. It's exactly what's appearing on the left. Okay. Okay, what is this one? This is something that you cannot really monitor on a real computer. Of course, this is just a simulation. Huh? This is a composer, it's a simulator. So you can just, we can just play, it's just an easy way to simulate, but it's just a simulation. Then when we have done our circuit, we can send it to the real quantum computer. Okay. On the right, you have some information like phase, real part, imaginary part, and probability of getting one. Of course, this is a Hadamard applied to 0. It's not written, but 0. Yeah, and so this is but these numbers are useful because they tell you some information about the state. Some other information about the state is the state vector. Some more information about the state is the state vector. Okay, what is the state vector? Is your wave function. So, which is the amplitude of the Hadamard state? 1 over square root of 2. Okay, so this is 0.707 plus imaginary 0.07. So here you have also picture that the state 0 and the state 1 have the same weight. Okay, then you have also representation in the Q sphere. The Q sphere is not the qubit, the block sphere. It's something else, has other rules, but it's done to visualize also multiple qubits. Okay. Anyway, this is kind of visual inspection. Okay. So what can we do? We can measure it. I added the measure. What happened? I added the measure. I had the wave function collapse. 0. Okay. Why 0? I don't know. This is by chance. Okay. We do it again. There's like another 0 again. And you see this is also changing. Let's challenge again. Okay, 0 again. If it's another time 0, why all times 0? All times 0?
So 0 here means it's measuring the 0th qubit.
Yeah, okay. It's measuring 0, but the state vector is collapsing on the state 0 every time. Don't know why.
Okay, so sometimes it will be 0, sometimes 1.
Okay, probably the random number generator is not a threshold. Okay, but then when we will see what happens when we perform several trials. Okay, so my suggestion is just play with the gates and see if they behave like you expect. For instance, how you would expect to behave that gate, and so on. So for instance, just work with 1 qubit. You can log in.
Yeah,
Okay.
I'm already logged in.
Ah, okay.
I'll just check. There's
There are also parameterized gates. Yeah. Like U. U is a nice gate. I just show you. U is a very nice gate. If you click on that, you have several parameters. These are parameters that can be used in a variational quantum eigensolver or something. So you have theta, phi, and lambda. 3 parameters. How did they work? You just click here, and they explain you everything. So this is the U. So if you want, you can personalize your gate with parameters and see how the state is changing on the qubit sphere. So with the U, U gate is parameterized. So let's come back to the composer. You have also parameterized rotation around X and so on. Okay. I want to delete this one. You see that even if I have 1 qubit here, there are 2 registers, means 4 lines. 1 register means 2 lines. I can also have T gate, S gate, Z gate. LMR and Z. Okay, please note on the left the difference between state vector and probabilities. If you use state vector here, I see 2 different colors. Why? Here, if I remove this, there is just 1 color. the probability is always blue. But it is in percentage. But the state vector can change sign according to the phase. Okay. So if I put a Z after Hadamard, what's happening? Which is the state? I mean, the Hadamard is the equal probability state, and what is doing the Z? What is doing the Z gate? It's changing sign to the second cubic. Sorry, to the one part of the cubic. Okay. So the red is the sign. Phase angle is not the sign, it is the phase. So phase angle pi, phase angle 0. So if you want to see more color, you have to. So one challenge would be now to see more colors, more phases. So you have to use different gates. Okay. If you use only power strings, you are not changing much. Actually, yes, you are changing. You can change that. Aha. Two new colors. What did I do? Mine is like that and strong. Yeah, because why it was why is introducing the imaginary part. Okay, so here if you look at the face, this is 3 pi over 2, and this is pi over 2. Okay, so that means. Okay, of course, if you have looked to probabilities, everything remains always the same, because the probability is always the same. Okay. Okay, so just play 1 minute more to this. What's happening if you put the identity? Of course, nothing. What's happening if you put the T gate? New colors are appearing. If you don't remember the T gate, I think you can. Okay, T gate is the one that changed phase. It's working on pi over 4 angle. Yeah, we have a pi over 4 angle. Okay, just try to do something and imagine what you expect to observe. You see, this is very compact representation of probability and phase. Phase is this one. So if you apply 2 times, it always changing color. What happens if I apply another Hahnemann? Ask yourself, what should happen when I apply another Hahnemann and then try? Okay. You should always in mind that you.
Okay, so now let's try to submit a job to the actual IBM quantum computer. So before submitting to quantum computer, we have to put a measurement because without measuring, it doesn't do anything. So just put a measurement here, a measurement gate. Yeah. Hello. 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 Yeah. So we have to always put a measurement on a qubit here before we set up and run. Then we just click on setup. So you'll see so there are three available machines: IBM Fez, IBM Marcus, and IBM Torino. Two of them have zero pending jobs, so these are the most free IBM quantum computers in our hands. So we can choose any one of them. You can change the number of shots here. You can increase it to see it, but first let's start with 1024. So I'm selecting Torino.
So this way you have 1024 times the same circuit measured every time. Okay, when you do such a.
Click on run circuit. You will see that there are view job details. If you click on it. So this is the status. It was not pending for any time. It has straight gone to the quantum computer. So you are very lucky. And now it's running.
No, that's seven.
So if you remember, we submitted just a Hadamard gate, but when you actually see the circuit that has been submitted to the IBM on the computer, it looks different because every time you submit a circuit, then it decomposes the gates with respect to the gates that is available on the specific machine. So these are the native gates available in the IBM Torino. And if you just go below that, you can also see the Qiskit code. So Hadamard is incorporated to RZ, Unix, and
Okay, you see that you had a Hadamard, but the quantum computer is not implemented in the Hadamard game natively. Okay, this is like when you are how do you say? I mean, even classical computer, you can control one complex operation with several smaller ones. And the quantum computer has a square root of x and fz as the 1 qubit gates. Okay, and so instead of putting Hadamard, you do this. You can one exercise that you can do actually that you have to do. You see that this is equal to the Hadamard. So what is square root of that? Up to you to search for it. What is that? Up to you to search for it. And just multiply that and see that this is that. Okay? This is for next time. I will write this assignment so that you can do that. That's very simple, but
Yeah, so RZ.
But at least-
RZ.
you get some confidence. So what it's actually doing, it's not exactly what you see in the picture. This is, of course, it's much longer than what expected. These are 3 gates, not 1. Okay. But that's the way this computer in particular is working. Another computer might have different native gates. So the native gates are different from computer to computer. I mean, the difference depends on the technology of the computers. But maybe even if they have the same technology, maybe it's implemented in a different way at the hardware level. Okay. So it is not strictly dependent only on the technology, it depends also on the computer. For instance, ION's computers, they have fantastic multi-qubit gates. Really multi-qubit gates, many qubit gates. Okay? Which is nice. And sometimes, but it's different than what we are using.
Oh,
These are native gates, so they can be implemented natively.
It's done, it's done.
Okay, this run. So why you have 4 qubits?
Probably because,
Because in your composer there was 4 qubits.
no, because the classical register had 4 probably. That's, I don't know.
No, this is the measurement outcome.
Okay, so, but there is this one qubit, one is register.
It's 1 qubit register. So probably the minimum maybe of qubit register is 4. And that's possible.
Yeah, yeah.
Sometimes you have like a minimum job, of 4 qubits and just 1. So
Yeah.
it chooses anyway 4 qubits.
Yeah. So as you can see, there's a lot of difference in the amplitudes of the 0 and 1 state. Yeah. So if you have 554 and 470. Instead of, like, I mean, it's not too bad also. Because it's just a 1 qubit gate, so the one, anyway, the fidelity of 1 qubit gates are good. Right.
Okay, you didn't see something strange?
No.
Okay. No, no, I mean, this is a. Okay. No, everything is normal.
I'm just changing it to one.
I know, this is, I think, okay, this is 2024, right?
It is 1,000. I will change it now. Maybe 8,092 or something.
Where is this? More.
Yeah, I'm changing this to one and then submitting it.
Can you see the result?
Yeah.
Okay, if you want to see the result again, view jobs, and you have the job.
The last one. Click on the instance. Yeah.
Here you have. Okay, no, nothing strange, sorry, I was thinking.
No, this is okay. I mean,
Okay, this is-
simulation is also kind of just like this. I think if you click on the gates below, we can also see the fidelity. No,
No. Okay. So can we change again?
number of shots.
Number of shots? Can you take notes of the numbers you get?
How do we know if the numbers is one or not? Well, 170 and not 500. More or less how much we do this. Something that depends on the number of blocks, right? And this dependence comes in. The average on the need depends on the number of samples. Okay, like what? It should be 500 squared plus or minus what? Something that goes as 1 over n? No. Yes? Sorry? No, it's going like 1 over square root of n. Okay? So the error should be reduced with the square root of sample. I like it because if you want to have a. Okay. Who did run this circuit? Come on, no, who did run this circuit? Just an hour at which point to run. So the majority of people didn't yet run this circuit. Okay, so we can go one step further. Okay, let us run with more. Maybe not run with the. I mean, just save your feet. Then you have something, but then. So we are running for you. I will probably run out of it, but doesn't matter. And okay, 7 seconds. Completion time. So not much.
So now it's almost equal.
Okay, now it's almost equal. Of course, this is 10 times more. 8 times more. So it's the arrow should be reduced by a factor of 2 square root of 10. Okay, very good. So we can proceed with 2 qubits now.
Yeah.
Let's go with 2 qubits. So run the birthday on your, I mean, create the birthday on your on the computer. How do you create a birthday? So first randomized and then sequence. Okay. Just another note. This cross here is the knot. That will be the X gate. Then it's just indicated as a cross as the C knot, but it's the X gate. Okay, now what you see is that
Entanglement.
yeah, there is an entanglement because you have 0, 0 and 1, 1. There is nothing on the others. Okay. If you measure, you only get one of the two. Measure one, you have to measure both. But the result will not.
So now it will be okay. Yeah, the result state vector is plus one.
Yeah, so the state vector inside only 0. Okay. Yes. So on the Q sphere, okay, this is the state. Let's remove this. So you see that this Q sphere allow you to draw visually different states, and we can put some phase here, and this change color. You know, and just randomly. Okay, this is rotating. The state is different. So it's not the same as the block sphere. Yeah, you are. Yeah, or probably. Okay, let's run this on the quantum computer. Now we have Marrakesh. No, wait, sorry.
Now you have to put the measurements.
Yeah, I have to put the measurements, otherwise it's not, I will not get anything. If you don't measure, you don't have access to anything.
And IBM Torino was 0 before, but everyone here is using Torino.
So we have, 14 people using Torino from Ghana, great.
they will observe an uncommon peak of usage from Mars. Oh, it's already done.
So it is done.
Yeah.
Okay, very quick. Okay, can we comment this output? Is it what you were expected to find? What happened? So you have 0, 0, you have 1, 1. 0, 0, how much?
519,
And 1, 1.
8, 11. Yeah, oh, 1, 1, sorry, 1, 1 is, 0, 1 is 8, 11, and 486.
So what's happening?
Yeah.
I don't care about the stage. How to go stage. Good thing, no? I mean, the fact that they are not balanced, 0, 0, 1, 1 is perfectly normal, but the fact that appears 0, 1, 1, 0, this shouldn't happen. Because the gate is the gate. So why is that happening? Because of the noise. So you see how the noise is important. Is the noise with respect to the number we have seen before, is the noise more or less as we expected? You remember that the first number I showed before, it was 2 times 23. That means 20 out of 1,000, which is more or less exactly what's happening here. So 20 times out of 1,000, the synod is failing. But it's not because the Hadamard is failing, because the single qubit gate usually has one order of magnitude highest fidelity than double than the 2 qubit stage. But it's because the Hadamard is failing first. You can imagine when you do many Hadamard, after a while it becomes a mess. Yeah. Okay. So another example that you can do is to put 2 Hadamard of different in different different direction. So you put one synod like that, then another synod like that. How you can exchange the knots? No, you cannot.
No, you want to put it below?
Yeah.
No.
I want to reverse.
Oh, okay, you click on it,
And you change target.
change the target.
Okay.
So for instance, this one, we have seen that this is perfect swap. Okay. But maybe we can, so it's a swap of, we should put a Z before maybe here. No, we should,
No, so,
okay, yeah, I mean, like swap.
we need, no.
Yeah, let's see if this is true. Okay. So here we have a swap and then a Z. So the first qubit is 0 and the second is Z. So it's 0. It's minus, it's minus 1.
So it will not
Yeah,
show.
it will not show. So let's put another map. Yeah. Remove the Z. Okay, the first is superposition, the second is just 0. So just measure and let's see what's happening. Marrakesh. Go. Takes time. Sometimes it takes time to transfer. I don't know, like.
Right? Are you getting confident with it? How many things to fix your idea of experiment? Change what is
Let's see if the jobs are ready. Yes.
Okay, we have 0, 0, or 1, 0. Okay, we have everything, but no main is. And we are seeing 4 numbers here because we are classical register at 4. Please check that.
Yeah, so it should be 0, 0, 1, 0.
0, 0, 0, 1, 0 are the main results. So you put on Hadamard, right?
Okay, yeah. So, yeah, I should, this is exactly, yes, the same. So the first two qubits, I mean, the first qubit on the right is half and half. And,
This one was.
sorry, the second qubit from the right is half and half. And the first qubit on the right is just 0. Okay. Okay. So what will be the next? We? No, I mean, why? Why the same result? So statistics is statistics. And then okay, there are many reasons why we don't get the same result. We'll say first is statistics because sometimes they will function collapse in one way, some other they will function collapse in another way. That is another problem. When you run, you are running on 2 particular qubits on the platform, which maybe are not exactly the same where you are running. Because there are better qubits than others. Now you have seen with the line. the color of the qubit is different, so that means the precision of the disk is different. So maybe you were lucky and you have worse qubit than what they done, then you get slightly different results. I mean, depends. It depends on the machine machine data. I think somewhere is written which are the characteristics of the qubit. You can also choose to send to specific qubits. I can check a bit. No, here, no logs. Okay. There's no information there. Maybe from the composer there is no way, but from the real backend, from the Python backend, there is way to get information about the qubit, how good were the qubits where I run, and which are the characteristics of the qubits where I run, and so on. Okay. Okay. Now, challenge for today is teleport. So. First, you have to, what do you need for teleporting? You need the birthday shared between Alice and Bob. So you need the 3 register. On the composer, just have a 3 qubit register. Okay. And then Alice, let's say that Alice is the first qubit. So first you have to decide which qubit you want to teleport. I don't know, I would use a qubit which is some characteristic, some color, not just Hadamard. Okay, some face, maybe Hadamard with some face. Or if you want even a unitary, a random unitary, I mean, a unitary like that, which is, which has theta like that, phi like that. Okay, very different states. So the state is a summary of the state is in this expression here. So this is 0.8. We have path 0.26 imaginary path, and the phase is 5.96. Okay, probability 1 is 24%. Okay, so this is the state I want to teleport. And then you have to implement the teleport protocol on the other two qubits. You go from the door on the electrons, right, and you find the teleport. Unically, the Alma, the gate line, and the same one I used, but the other one. This is your own state. It's your first teleportation. So please choose the nice way to say you want to. And from time to time, just have a look to the Python code on the right. So there is some import of libraries, creation of quantum registers. For instance, now I have two registers, one quantum with 3 qubits and one classical with 4 qubits. Okay, I don't want to drive for you I have to tell you something about, because you remember there is one part which is a bit delicate in teleportation, which is that you have to apply a conditional gate. Remember teleportation? Reporting.
Yes, yes. It's also in the lecture notes.
Ah, yeah.
Laboratory of quantum physics. Yeah. Yeah.
Oh, okay, but there is no, except secret. Okay, this is exactly what we had. I can show you again if you don't, you please write it down. So you remember Alice create a state. So you start creating a state. And then you have a C naught. But here you also have another state, the best state. Now these two qubits you have to create the best state. And this is a generic state. And then you have to do this. The only tricky part is to make this conditional. This is x to the m2. So once you are there, I will show you how to do it. But in order to show how to do it, you have to copy this because I need to. Okay, because the question. So the first qubit is at your choice. Sign there is what you want to choose. The best page. And then it starts the different with measurement. Right now, but
But the sound was single. The first impact that you realize when you work on Apple is really full of errors. Yes. How is possible? That's why we actually really put down to that. Otherwise, they, let's say that, yeah, 5 or 6 years ago when I started, it was 101 in the world. Completely perfect. So really not a problem number. So, yeah, fine.
I have to show you how to do the conditional gate. Why there is this stupid stuff. Okay, sometimes it's also used for, I mean, you can modify the Qiskit code, or you can modify the OpenCast code. Okay. So to change name here. No, it's not changing. Now these are linked to the composer. You can add those.
That we have to first create a build state that they're not.
Okay, please, you have to create the best state here. Okay,
Because these are initialized to 0.
this one, this beta 00 is the best state. It's not explicitly written. So if you want to create the best state, you have to create actually this form. Otherwise, you know. This is the best state shared between Alice and Bob many times ago. Okay. You see this one is, it's longer than the others. Why it's longer than the others? Because this takes more time than the others. Because it has 3 parameters, and so it's doing several. If you see there will be a lot of gates translated inside. So I don't know, I like to have classical registers with only 1 bit. So I'm just deleting the bit because it's a bit confusing the fact that the classical register has more than 1 bit. So instead of having one classical register of many bits, I would like to have 2 classical registers, each one of 1 bit. I mean, just the way I. Little bit. Other register. Okay. Now, for edit. Little bit. Manage registers. I call it CA and CB. And then. This one. Okay, so this one is going to X to this and then to that. This is X. It has to be connected with this register. Then you also have the other one. So X is connected to this register. To do that, I click on if and apply that. And then I have to change because it's not this, it's the other one. It's a bit tricky. So this is the other classical register. Okay, and then Z is the other classical register. One thing that I forgot to say, but now it's too late, is to take note of your initial state, because it's the one that will be teleported. So do you remember how was your initial state, more or less? Outlook, colors, and probabilities.
Conditional if,
Yeah,
you have to check if it is the correct classical register, if it's checking. So you have to check. Okay. And it should be equal to 1, the value. And so-
ah, yes, right, it's not equal to, the value is not equal to 0. Because if this is 1, you do the x. If this is 0, you do the x. So you translate this x to the power of something into an if condition. Okay, so instead of doing x to the m1, you say that if the measure m2, sorry, if the measure m2 is 1, you apply the x. If the measure m1 is 1, you apply the z. And you can do, you can make this first by drawing x and z, and then by applying this if gate here. But the if gate has to correspond to the correct classical register. So this x has to be attached to this, and this z has to be attached to that. But the condition is wrong. So you edit the condition because the condition has to be, the gate has to be applied if it's 1, not if it is 0. And then something went. I put to remove it instead of. Okay, so now, for instance, this should be attached to this. So I'm just doing like that. If by default is attached to the first classical register. Please note that I changed this register. Before, by default, you have one classical register with 4 bits. But just for clarity, by clicking and modifying, I create 2 classical registers, each one with 1 bit. CA1 and CB1. So the only thing that I have to do is to change this. This is Q2, okay, it's fine. And the classical register is the other one, and the condition is 1. Okay, now you have Hadamard, CNOT Hadamard, 2 measurement, and everything.
Oh, missing one gate. You created the bell, then you.
Yes.
The signal before the
Yes,
other one.
yes. So because this bell here, this CNOT here is still attached to that. Okay. So I'm missing one gate. So I take the opportunity to cancel this now. Just because I want to check this state. So this is my state. If I cancel this, this is my state, you see? I just want to have a picture of this. So I will remember 23.8% of probability of 1, and this picture here, this phase and this filling. Okay, so now I will put again this, and I will put also the scene. Because now when I put this, this is not a qubit anymore. See?
Before the Hadamard.
Yes, sir. It's before the Hadamard, but after this other Hadamard. And where is the other Hadamard? Yeah, I just remove it. Come on. Okay. Hadamard.
The CNOT.
Why not? So.
CNOT move down. Out. You get the Z code. The Z is that side.
Yeah, but this is. It's not the stage.
No.
Teleport is not working. No, because I this was my thing. This is the false thing.
No, the writing problem is, can you show me the picture of that? The X should be from the second key, and you have put it in the first.
X. The. In the second.
Oh, it's in.
That's in the first key. Yeah, but this is wrong.
Oh, we have to measure it, right? No. we don't. But you can work.
How far did you go? You have this? You have some problem? Teleport is seems not. Working. Because if I remove this one. Oh, but this state is also different with respect to the other one. Why?
Yeah, I get it.
But maybe I didn't have one.
You, the Hadamard when you saw the state after a year. So when you remove those measurements.
Yeah, 100
One Hadamard.
Yeah, you're right. So I have, so before I didn't have Adamel, I have something else, I have T maybe. So you remove the Adamel,
The Hadamard, yeah.
it's not this one. Which state I have?
Just you, I guess.
Okay, just you, let's say just you. Okay, let's say this is my state. 95% one. What is the boring state? That's not.
You have to change the phase.
Okay, and then, so this is my state, it says, it's tricky, it's not so, this is my state, 954%. Then if I put a Hadamard here, and then I measure, and you see now, this should be before the Hadamard, yes, you're right, okay. Open the mode. Yeah, it's not the best, I mean,
Yes, coding is better.
coding is better, yes. Okay. Okay, now it should be fine. Yeah. No, 54%.
There's some here in
True.
the page.
How you know? Excellent. Well, what is the problem? Just try to have same thing with some computer to see how.
So we have all 5 by 2 here. All you have changed 5 by 2. Point.
Some things. The probability is fine, but then some things.
So I did your one, so 0.3, 0.4, 0.82. No, oh, the first one is point.
0.4, 0.3, and 0.8.
Okay. State is 0.533, 0.6. So I guess you've got it. So you just check the last. Is it the same? Yeah, it's the same.
Okay.
Oh, we sorry for.
Yeah, it's working. We have teleported this stage
We can.
at least in the composer. So we have a state which is, let me see.
Now the second. Wait, wait. This one. Yeah.
Okay. No,
No, no.
you close it. No, okay, this one. Okay, so the state is this one, and it was actually what it was before. So it's 909.54% one, and also phase and so on. So now what can we do is to go on the quantum computer and see if it's working. This is real teleportation, not a state teleportation. Okay. But of course, we will not have access to the final state in the quantum computer. What can we do? We can just measure maybe the probability and see if it's something similar. Okay, so we will add one measurement.
I'm just saving it so that we don't lose it.
Yes. We will add one measurement at the end. So who was able to do this? It is not easy because we want something and he has to have. Thank you. Very good. So now I will just add another classical register. No. I will add another classical register. This AS1. And make one additional measurement just to check the state, okay? Measurements on the third register, and this will go here. So now I can submit this. Marrakesh. Okay. So I can just take only the same on another tab, press the on this, and check for now. It's right? Yeah. Why is valid secrets?
What is going?
I think they. Six of hundred. Otherwise, I think I will.
Well, so let me start to.
Ah. Okay,
So I think we have to. Find the right method. For you say one is file. So if you go file and put save, you can save your file and then tomorrow you can load it again. So then we can continue with this. Okay, because not everyone was able to teleport now. We want to have at least 50% of teleport success. Okay? So see you tomorrow. Thank you.
sorry, it's not tomorrow, it's the day after tomorrow. So we can have a small break. So you have 2 nights to try it alone.
Yeah. Guess what?
Yeah.
Already started. Should be already started.
You have to join through Zoom. You have to join the Zoom so that you share your.
How do I join this?
So you go to Zoom, then we have the meeting, and we have the password.
Should we have a break?
Yeah.
A break?
Yeah, short break. John. Yeah. Yeah. Meeting ID 915 8295 8484.
4.
Yeah. Then you just join. And passcode 7571 62. Yeah, join. I share. What's 9?
We have a power plug. Questions, working.
Not sure if
To show that we have a break, short break. Will take a while until I set the break. Okay.
What?
Please point that. Stay in front of. Okay.
Yeah.
No working? Oh, no, it's okay. No, it's okay. Okay.
Angela? Angela, is that?
Yeah.
You want to say something?
No.
Okay, so how long? Roughly?
Yeah.
Hello. Hello, everyone. So we're going to start. I'm Eric. I'm talking about quantum machine learning today. Please ask questions, right? So maybe if you remember the first speaker, Tomaso, he was very clear about that. There's no bad questions, right? So please let me know, because then I have to see where I'm going too fast or slow, right? So if I'm going too slow, also tell me. All right. So I'm working at Continuum. So it's a quantum computing company in London, or globally. So lots of offices in the US, in the UK, a little bit in Germany, and in Japan. Okay, working there. And yeah, as I said, so today I'm going to talk about quantum machine learning. And I just want to, is the sound okay? First question. Yeah. Everyone hears me. The last row, sound okay? No one. Huh? Okay. This is like a sort of a middle. In the last row, there's no one reacting. But anyway, maybe they don't hear me. So this is a lot of notation. We don't go through this, but I guess you have access to the slides because I uploaded them in a folder. I'm not sure. So if you want to have a look again, then there's a collection of notation, but it's going to be introduced anyway as we go along. I wanted to start with a little primer on Pauli matrices and multi-qubit Hilbert spaces. So I guess this is something you already saw in various forms in the last couple of days, or maybe anyway have a background about this. Actually, okay, can you raise your hand? Who knows Pauli strings and multi-qubit Hilbert spaces? Like before this week, who knew this stuff before? Anyone? No one? A little bit? A little bit? Okay. Do you know Pauli matrices? Pauli matrices, a little bit more? Okay. So I printed the 3 Pauli matrices and the identity, which is sometimes put into this set of Pauli matrices here, right? So, and the important thing is that they build a basis of the 2-dimensional operator space. So any operator over a 2-dimensional space, so mapping from C2 to C2, can be represented as a linear combination of these operators. And the same thing holds for the multi-qubit Hilbert space, but then we don't take a single of these, but we take products of these Pauli matrices, and this is what is called a Pauli string, but we come to this. So the single qubit Hilbert space is just 2-dimensional space, right? And we're always working over the complex number, so it's complex 2-dimensional space, C2. This is something which you saw. So the basis vectors are 0 and 1, right? The cat with a 0, the cat with a 1, and every single qubit state you write as a superposition of these 0 and 1 cats. And now the multi-qubit space is taking the tensor product of the single qubit space. And this is basically, again, a complex vector space, but now which is 2 to the n dimensional. So you take the product of these 2's, right? No, actually, you take the exponent, sorry. So you take 2 to the n. And actually, the mathematical theory behind tensor networks is pretty deep. So we don't go into this, of course, and this is something which, I mean, in quantum computing, anyone is very accommodated with using this sort of notation, but actually it's a bit tricky. But it's much easier to visualize these things as these string diagrams, right? So a single qubit system is just a string or just a single line where you apply gates. So for example, an X gate here, which is exactly this one, right? So this line represents 2 dimensions. A multi-qubit here, 3 qubits are 3 lines. Each of these lines represents 2 dimensions, but the 3 lines together have 2 to the power of 3 dimensions. So 8, right? And this is now a Pauli string acting on these 3 qubit state on this 3-qubit system, where the Y operator is applied to the first, the Z to the second, and the X to the third. So these little indices here, they do not say this is a different operator. They indicate, okay, this operator is applied at the second qubit. Right? So the 1 here means first qubit, 2 means second qubit, 3 means third qubit. The lines we always count from top to bottom, right? 1, 2, 3. This is a common convention. Some people do it differently. And here is how you would write this Pauli string. So this P here, bold-faced because it's a, let's say, a vector quantity, is exactly this one here. Y on the first, Z on the second, X on the third qubit, right? So this is a 8 times 8 dimensional matrix. So usually, if I would be very precise, I have to write tensor products here in the middle. But I'm not doing this because this is a very typical notation everyone is using. Right? So the indices indicate on which of the factors, so on which of the line it's going to happen. And this product is, let's say, an 8-dimensional operator. And now, as we had before, any n-qubit operator, so acting on 2 to the n times 2 to the n. So every matrix, which is 2 to the n times 2 to the n dimensional, right, a very big matrix, can be written as a linear superposition of these Pauli strings. And therefore, the Pauli strings are very important because they are sort of a operator basis and they come up later. Questions so far? Please, I'm not going on without at least one question. Yeah. You can. These things are just convention. So it's just important that you agree on a convention, right, and stick to this convention, because otherwise, basically, if I would count from bottom to top here, right, then the X would have the 1, the Z would remain to have the 2, and the Y would have the 3. So this would be actually a different operator. It's actually not so important that the positions of these things are the right positions, right? It's not a problem to have here 1 at the last position, let's say. But yeah, this is just a convention, so you have to stick to something, communicate it, this is my convention, and then because this, I mean, yeah. Thanks. All right. Then what is quantum machine learning? A little bit. So any ideas? Who knows what quantum machine learning is? Maybe someone from the 3rd or 4th row? Yeah? Is there someone? No? All right. So quantum machine learning is either machine learning with a quantum computer or using quantum, well, okay, anyway, I go through these 4 options. But I mean, it's of course at this intersection of machine learning and quantum. So machine learning is a very big field in the last 10 years, right? So it started with these machine learning models which could discriminate between cats and dogs. I guess every one of you heard of these things, right? You put in an image and then the machine learning model tells you, it's a cat or it's a dog. Sometimes the models can even generate new images of cats and dogs, right? This would be a different application. And nowadays, they are especially famous for these large language models. So they produce text, but actually anything. So they produce also code, program code. They produce papers. They produce, I don't know, they even produce pictures, even though it's a large language model. I don't know. But yeah, and sometimes people call this AI then. These more, I mean, the point is a little bit, these large language models, they are really huge and they basically trained on the whole internet, right? And this is a bit different to what happened like 5 or 10 years ago, where the amount of data was very small in comparison to the full internet. Question? So, okay, there are a couple of overlaps between quantum and machine learning. And this picture you often see actually. So on the x-axis, you have classical algorithms versus quantum algorithms. Quantum algorithms, you saw already a few of them, right? These are these pictures with the gates, with the lines. You just You just did one of these algorithms doing teleportation in the previous lab, right? Classical algorithms are classical algorithms, what you do when you program with Python. Who's familiar with Python, by the way? Some hands? Python programming language? Okay. So we're going to use this in 2 days in the tutorial. And then we have the y-axis, which is data, classical data versus quantum data. This year is just standard machine learning. It's a classical machine learning algorithm which is applied to classical data, such as images of cats and dogs, or translating a German text into an English text, or whatever. This year is a quantum algorithm applied to classical data, and this is actually the part where we're mostly considering in this lecture. So a quantum algorithm, in this sense, is a quantum machine learning model. So it's a circuit which has parameters in the same way as a neural network has parameters. And to solve a specific task, these parameters are optimized, or people say also trained or learned, and so on, right? So the spirit is very similar. It's a model having parameters, and I'm training the parameters or optimizing the parameters. This is all meaning exactly the same thing, such that the model produces, let's say, the mapping images to labels. This is a cat or this is a dog. But the model specifically looks a bit different. So the neural network, you saw, most of you saw the picture of your neural network, right? And these parameterized quantum circuits look a bit different, but in the spirit they're very similar. Then there's this corner here, which is classical algorithm applied to quantum data. So you could imagine, for example, you take a classical machine learning model, a neural network, and you feed into this network quantum states or some representation of a quantum state. And the network should tell you, is this an entangled state or is it a separable state, for example. So this would be like the cat and dog situation, but with a quantum property, right? It's not a cat and dog, but it's like, is it entangled or is it not entangled? So this would fall into this category. And then, of course, there's QQ, which is using quantum model to work on quantum data. So you can also consider this again. You want to discriminate between entangled and separable. But you're not using a neural network, but you're using a quantum machine learning model. So, yeah. Say again? Yeah, so the question was in which situation we are here in this stages. Mm-hmm. You mean the field, right? I mean, how is the current state of the art in doing these things? Okay. So yeah, the question was, okay, what is the current state of the art of this box, basically? What are we able to do with classical algorithms in terms of quantum data? And well, I mean, the difficulty is that the quantum data is an exponentially large quantum state. So we usually cannot insert this into a classical machine learning model. There's something which is called classical shadows, or more generally classical surrogates. So the idea is to have a compressed representation of the quantum state, which is approximate. It's a certain approximation of the quantum state, but needs only polynomially many, let's say, memory to represent, and in comparison to the exponential. And then, of course, the question about what the state of the art is. I mean, this is difficult to answer because this is a very active research field, so people are doing all the time very interesting stuff about this. So I would say the general, I mean, this example here really, with very high accuracy, separating between entangled and separable state is a very hard problem. And I don't think there's a machine learning algorithm that solves this problem for large systems. So I've actually worked on this a few years ago, right? And we were considering very, very small systems, and it was not perfect. I mean, it's having, yeah, but I mean, this is a very hard problem. So, yep.
Just wondering, the fuzzy algorithms, you mentioned that they are parameterized quantum circuits.
Yeah.
So is there any way of transferring some of those parameters to train?
Yeah. So the question was if we can infer or train some of the parameters of this parameterized quantum circuit on classical hardware, right? And we come to this point later, and there are several layers about this. So I mean, the standard architecture is actually training the parameters on a classical machine. What actually there are more modern versions where you not only train the parameters on a classical machine, but you actually train the full model on a classical machine, which for some reason is possible, even with polynomial overhead, right, efficiently. But then to carry out the circuit which you have learned, you need an actual quantum computer to do this. So this is something we actually don't touch here, just in the very end, if you have a few summary slides of these things. But this is a very important topic because you want to push as much as possible to the classical hardware, because classical hardware is much cheaper than quantum hardware and currently also much faster. So, and just much more, right? Tons of supercomputers around the world, and I don't know, there's just a handful of quantum computers, and they are pretty small for now. All right, thanks a lot. Then let's go a little bit into machine learning. Is it actually the tempo which I'm talking, is it good? Do you understand me well, or should I talk slower? No, or good? Yeah. Statistical learning theory. This is basically has been developed, I guess, already in the 80s or something, so really 50 years ago or something, which were one of the beginnings of trying to formalize machine learning. And at that stage, we didn't have the computers to do it actually, these machine learning things, right? This was just theory development. It's a little bit like we do now for a quantum computer. We didn't have the machines which actually can solve these learning tasks. But then in 2010, 2015, we had at some point the hardware, and then this whole field, became very important. So we always consider an input and an output space. So we are considering what is called supervised machine learning, where you train a model on a supervised task. So for example, you have images and you have labels given. Okay, this is a cat, there's a dog, there's a whatever, antelope. So apologies, this cat and dog stuff will appear very often. It could be also text, right? It could be text, a very long string of text, and why it would be, okay, this is a political text, or this is from a newspaper magazine, this is about sports. This could be also a model which can feed in a text, and it tells you, that's a sport article or something. And these, so it's a finite data set. The size of the data set is big N. Little n is the number of qubits, so it's a different number. It's big N, and these are pairs of input and output. And often these outputs are what we call labels, but not always. We come to this later. And these data points are sampled from an unknown distribution. So we assume there is some distribution which fixes how do cats look like in reality, right? How do pictures of cats look like? And correlate this with a label. Okay, this is a cat, this is a dog, and so on. So we assume that there is this distribution. We don't have access to it. It's not known to us. But in principle, this data set is drawn from this distribution. And this is a distribution acting on the product of X and Y. So each new point you get from the distribution is a tuple of one Xi and one Yi. And each of these spaces can be multidimensional. So I should have printed these X's and these Y's in bold figures. So actually these are vector quantities. Xi is a vector, not a one-dimensional number. And the goal is to learn a function that represents the distribution in a sense that it's approximately giving Yi for each of the Xi's. And now the very important point is that we are giving a training data set, right? But this function which is trained should ideally perform well also on new data points drawn from this distribution. So we train this model, I will talk more about this in a second, on the data set that is given, which is just a subset of the distribution in a sense, right? So we want to, the big goal and also the hard thing is to have an F which is performing also very well on new generated xi and yi, which have not been part of the training data set as. And then the question is, okay, how do we learn such a function? And this is called a hypothesis class, which is basically just a class of parameterized functions. So we want to solve this on a computer. This means we somehow have to make the problem finite. So we cannot search over all functions because this is an infinite problem. We need to make a small set or smaller set of functions which are parameterized by a finite number of parameters. And then this is something we actually can run on a computer. And this finite is, of course, can still be very large. You know, these large language models, they have, I don't know, a trillion parameters, a billion, but yeah, it's really very close to infinite. Not quite infinite. Right, so an example is the typical density forward neural network with a certain number of layers and a certain number of neurons per layer, right? So this is an example of a hypothesis class, and then I search for one of these H's which are represented by these neural networks, which is the best approximation to my problem. Right, I actually have a picture of the neural network here. Does someone know how I can move this away? The pen? Oh, okay. Thanks. Okay, how do we actually learn or train the model? This is always correlation in terms of a loss function. So this little L here is quantifying the distance between the prediction, H applied to our input, and the actual output, right? So for the training data set, it would be xi and yi here. Here are just 3 examples. The first one is called 0-1 loss. This is 0 only if H of x is exactly 1, y, and then this is from 0 and for all other cases it's 1. So this is a very strict loss function. Actually, it's not differentiable. It's not even continuous, so actually it's not easy to train this function. More common functions are loss functions, for example, quadratic loss, where you take the distance between these, between the prediction and the target, and take the square of it. So it's always positive, but gets smaller the closer these two values get, right? So this is what your loss function should have as a function. And the absolute loss is also very commonly where you don't have the square, but you just have the absolute value. And then you define something which is called empirical loss or empirical risk, which is the sum of the loss function evaluated on all points of the data set, of the training data set. So I, from 1 to n, this is actually exactly the training data set, and you can put this normalization factor if you want. And here you have to discriminate between the empirical loss, so empiric for based on the data I have, versus expected loss or expected risk, or sometimes also called generalization error, which is also the distance between predictions and targets. But now you're not averaging over this finite set here, but actually you're averaging over the full distribution. Right? So it's a little bit a mathematical term, but you have to imagine this is an integral. You integrate over the distribution, right? Or more maybe more intuitive, consider that you have an infinite size data set, right? Your data set is actually so large, infinite size, that it basically hits every potential combination of xi, yi in the space x times y. And then this here is going to be an infinite average over all these things. And what you want to have is to train on the empirical loss, but to have a low value of the expected loss, because this means generalization. You actually can also have good performance on unseen data, right? So this is what you usually have. You were giving like 1,000 images of cats and dogs, each coming with a label cat and dog, right? You train on this, and then you want to use this model to apply to new Who is it? Please stand up. Anyway. Right, so you want to, now I'm giving you a new image of a dog, but the model should be able to decide, that's a dog. So, sorry if I make this point really clear, but this should become very clear. And this is really the hard thing, right? To have a low generalization error. You can define something which is called a generalization gap, which is the difference between these two quantities, but it's not so important. And learning is really meaning, okay, finding this specific H, which minimizes or as far as possible minimizes the empirical loss. And then ideally, there's a lot of theory about this, also have a low expected risk or generalization. So I've been speaking a lot. I've been speaking a lot about cats and dogs now. This is, of course, the typical classification problem, right? You have a certain number of classes, and the model should be able to classify new data. And classification means that the output space Y is a finite space. So just has, let's say, 3 classes or 5 classes or 2 classes or maybe 20 classes. Now you can also consider continuous output space. And this is more the what we usually call function learning or regression. So basically, you could imagine that your xi's are all somehow distributed on the interval 0 to 1, right? And you have an unknown target function, f, which is maybe a complicated superposition of sines and cosines, right? So some wiggling function. And now you're, for each xi, which is the point on the x-axis, you have a prediction of yi on the y-axis, but it's a continuous y-axis, right? And this is then not called classification usually because you have infinite many potential output labels, but this is more what you would call function learning. And we have examples of both of these types of let's say, fundamental problems. Okay, question? So the question was, what are the disadvantages of training a classical problem on a quantum computer? So it's about training a classical data set on a quantum computer, not a classical computer. So the one big disadvantage is, of course, that the quantum computers which are currently available are very noisy. So, and they are small in comparison to classical computers and supercomputers. So at the moment, we cannot compete with these quantum models with classical models. The advantage is that the quantum model is in principle able to process an exponentially larger vector than the classical model. Right? So if you look, but of course this has to be also taken with a grain of salt and so on. But in principle, you might expect that, let's say, in 10 years or whatever, at some point where we have large machines, these large machines can actually perform better than classical computers because they have a better scaling. For very large problems, they actually become better. So, okay, the question was if you consider a rare disease data set, if you should better rely on quantum classifiers. So there are 2 different means of large and small here. One is the size of the data set, which you can. The other thing is the dimensionality. Yeah, but so quantum models can be beneficial in D, so the dimension is very large. Right? So in principle, they can be beneficial, but not nowadays, because nowadays quantum computers are not big. Right? So if you want to solve an actual real-world problem right now, a quantum computer cannot yet solve it because the machine is too small. Yeah? And it's more like, so what we do at Continuum and like other companies as well, right, is finding potential candidates right now, which have a good promise that in, let's say, a couple of years, quantum computers can better investigate. Like quantum models can better investigate. Yeah. So two things, like well, there are like there's exact simulation, right? There's emulation, which is trying to represent the noise model of the actual hardware, and then there's hardware, of course. So let's say if the emulator is good, right? If the emulator is actually a good representation of the hardware, the output from the emulator should be very similar to the hardware. But of course, if you can tune the noise of the emulator, or if you set it to 0, you get to the exact classical solution, right? You don't have the errors. That's true. Right? So you circumvent the errors. But now the problem is that you're simulating a quantum circuit, which is in principle exponentially large, high dimensions. Right? And so there's no way that you can achieve a quantum advantage via classical simulation, right? Because classical simulation is again is not efficient. So the only advantage is at some point using an actual quantum computer, which is less than this. Yeah, there is a question. I hope the rows in the back are also following. Okay, so now a little bit more about the parameterized quantum circuit, right? I was telling you here basically about generic statistical learning theory where the hypothesis class can be anything. And now our hypothesis class is the set, let's say, of parameterized quantum circuits with a given architecture. So this here is an example of an hypothesis class. It consists of first an encoding layer where your data set is encoded, let's say the image, right? Or your text. This is somehow written on these many qubits here. And if I'm just using 3 lines here, this doesn't mean anything, right? Imagine these are n lines. So this is just an example. You have the 3 lines here. And then you have a parameterized block where, for example, these 2 gates don't have a parameter, but these 2 gates have a parameter, right? And for each value of these parameters, this here is a different model, right? And all these models together build a hypothesis class. And now I want to pick those parameters which best approximate my problem, so which are the optimal candidate of the hypothesis class. And here we have a measurement, so this is normally denoted by this, right? It's just an abstract notation, but what we mean by this is to measure an expectation value of an observable. Observables are usually denoted with A, so this would be the A here. The unitary here is the symbol for this data encoding and parameterized block at the same time, depending on x and theta, right? And psi 0 is whatever initial state you put here. Often psi 0 is just a 0 state. And any qubit initialized with a 0, but yeah, there's a lot of variation. So we have 3 steps. We have data encoding, we have parameters, and we have the measurement. But then, of course, there's a lot of variability. So I can take 2 of these blocks together, right? I can even interleave encoding and parameter. So I could have several layers, encoding, parameter, encoding, parameter, encoding, parameter, which is not ordered in this way. And we'll have an example later today about this. And just to pictorial represent this. So this is just the image I showed you, but you could also imagine, okay, actually this full block here in the front is a parameterized data encoding unitary, right? Where I put both the x and the theta at the argument. Or I could also speak of a encoding layer and a parameterized measurement, which is like measurement A, but transported back via the parameterized gates, right? So this is all exactly the same expression. It's just a different sort of interpretation, let's say, or a bit different. It's just naming, let's say. Am I talking about a parameterized observable, or am I talking about a parameterized unitary and an unparameterized observable? This is really not important, but you see all these different things, and you have to know that these are all the same, basically. So this is the, for example, the parameterized and data dependent observable, right? I just call everything observable now. Can be done as well. And as I said, like x does not need to be before theta, right? So you can have interleave of these x's and thetas. You can first have theta and then x. So, okay, a few points about data encoding. So this is the first step here, this pink box. Okay. Now, for now, we assume data encoding just happens at the beginning. As I said, it's not always the case. But there are a few encoding strategies which are called, for example, basis encoding or amplitude encoding. Actually, there are, let's say, hundreds of different encoding strategies. So there's a huge number, but there are a certain small set which are the most common ones or the default ones. So the basis encoding, you usually consider that your data is binary data. So your x. Okay, now I have to apologize a little bit for the index I here. So the index I before was referring to the data point, right? Here I refers to the component of the data point. So I should write this y, this I should be a top superscript ideally. Okay, so apologies. But the point is, let's say each of these components of the x is just either 0 or 1, meaning that x is the set of all strings, of all bit strings, right? This is called a bit string, a string of just zeros and ones of size d in this case. And what I'm doing now is to encode this data x as the cat vector where each qubit is either 0 or 1, depending on your data. So I show you a picture. So these are binary images of digits. So that's the famous binary MNIST data set. So MNIST is one of the first classification data sets or benchmarks which people used 10 years ago. It's about, okay, getting an image of this kind, and the model should predict this is a 4, this is a 6, this is a 9. And this is binary MNIST because each point, each pixel in the image is either 0 or 1, right? 0 would be white, 1 would be black. So now the number of pixels in one of these images is apparently 28 times 28, okay? It's from the internet. So there are 84 pixels in one of these images, right? So the dimensionality, the D is 700 something. And each of the x's is you just go here row-wise, right? Tuck, 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 right? You just concatenate each of these rows into a vector which has 700 something components. And each of the xi's is either 0 or 1. Okay? And now, exactly this list of zeros and ones is what you write in the quantum state. So this is a very long cat, right? It has 700 something x's here. So who knows how many qubits I need for this? Qubits. For that cat of this size. No, it's just 784. So the length of this here is just again 700 something. So, but it's still a large number of qubits. Okay, questions about this point? Who understands how such a pixel, how such an image of pixel is converted into the cat? Please stand up. Who understands? Well, one understands. Someone else? Okay, so most people don't react. So maybe the gentleman next to the camera. Can you tell me? Do you know how the pixel image is converted into the text? The question is that you have this fixed image, and how do you convert it into a cat vector? Which is better. You have a very long vector, multi-vector, just 0 to 1. And this is exactly what you write into this cat like stage. So, and then it means you need as many qubits as you have components in your flattened array. Okay. Oh, okay, right. So what I want to show you here is that you need a very large number of qubits to encode such a simple picture, right? Because in the basis encoding, the number of qubits is the same as the dimensionality of the vectors. So it's not making use of the exponentially larger distance. Not a good choice. She's saying it's a waste of resources. I mean, nevertheless, in some situations, this is a good encoding to choose. Depends a little bit, but in general, it's really a waste of resources. The question was, how can we represent floating points? So you can answer this. How would you represent floating? How would you represent a single floating point? Okay, so you convert it to a binary, right? So you're fixing the length of the bit string. Let's say with 5, that's a bit string of length 5, you have a discretization level with float of 2 to the power of 5, right? So you are basically so you're discretizing your one-dimensional float number with 32 discrete numbers in between, and then a specific bit string like 1001 would represent a specific number. Right, so, and this is what you have to do. Right. I mean, actually, not even color, but grayscale, right? The first thing is grayscale. If you have color, you have usually three color channels. So you don't have one float, but you have 3 floats for each pixel. Right? You have you just have to organize your cat, right? And remember which position of the cat you wrote these different. But this is exactly what's happening on Classic. So, but the thing is that on a quantum computer, we ideally can do something better. And one thing to do better is the amplitude. Not always, right? It's not always just one thing fits it all. It's always dependent on the situation. But the amplitude encoding is representing each of the components of this vector as the amplitude of the ith basis vector. So you have let's say 5 qubits, right? Your Hilbert space is 2 to the 5 dimensional, 32 dimensional, right? And your basis of this vector space, that size 32. right? So, and now this is again a convention. And if you're a NumPy, you should know Python, the modus convention. So I usually starts for me at 0, goes to G minus 1, right? So the first entry of vector is the square 0. This is just one entry. So basically, okay, for 5 qubits, t would be 32, right? And we can encode 32 of these xi's on each basis vector, and on top of this, each of these xi's is a float one. Right? The xi does not need to be binary, but actually can be something between can be a float. Then I just have to normalize the full state of this vector to ensure that the full state has normalized. This is this vector n here, but in principle, each of these xi's is an arbitrary thing. Now you see this picture here of cat, right? This is the number of pixels. So it's roughly 21 million pixels. And now if you take a logarithm of this number with basis 2, we have the number of qubits, just 25 qubits, right? Now you see, okay, this huge image compares to this, right? And you see the difference. 700 qubits in one case, 25 qubits in the other. This is the exponential advantage, which everyone is hoping for, right? It's hard to actually get it, but principle. This is it. So yeah, we want to, and this is not a waste of resources, right? We want to use the full dimensionality of the Hilbert space to encode this, just 25 qubits. All right, and this is something you cannot do classically. Classically, you have to do this. This is what you do classically to encode data on bits. Right? Cool. So then there's one more encoding. I don't want to go into details, which is called Hamiltonian encoding, right? So in the amplitude encoding, you were encoding the data components as the amplitudes of the state. In the Hamiltonian encoding, you're encoding the data components as in a Hamiltonian. So, and this is basically, I think you had a lecture about Hamiltonian simulations, correct? So this is now for the quantum mechanical concept. It's not easy to understand. Maybe in principle, you can generate every unitary by taking the imaginary exponential of an operator by Hamiltonian, right? And the other way is also true for any Hamiltonian. The Hamiltonian has to fulfill certain properties. And this one here is a unitary matrix. Now I can make H data dependent. So this is an example, right? Where I just have, where I just put the xi's and xj's as the factors, as the coefficient of z i's and j. This is again a point string. Right? So z applies to I qubit times z applies to j qubit. And now who can tell me how many qubits do I need to encode a vector of t with this Hamiltonian? There is someone from the back. The chance. So it's T again. It's bad again, right? But this is because I picked the bad Hamiltonian. So here I need again n qubits to d qubits to encode these t values. But in principle, the Hamiltonian, and this is what I told you before about polystrings, is the sum over all polystrings. The number of polystrings is not t to the n, but 4 to the n, larger than what we saw before. Right? So you can basically go through all these 4 to the power of n different polystrings, right? It's a string of base n, and on each position you have an x, y, z, or an I. Right? 4 to the polystrings. And each of them gets coefficient dependent on x. For example, one component of this, then you can find a huge number of components again in this Hamiltonian, and then this unitary is encoding this data set. So that's just for now. Okay. So much about encoding. So coming back to this picture I showed you here, this was all about this first pink box here. Okay, so there's more stuff to follow. So this is the typical pipeline how you train a parameterized quantum circuit or a quantum machine learning model. So you have a classical data set, as I said before, X's are images, Y's are labels of cats and dogs, or X's are values on the X-axis, Y's are values on the Y-axis, and you want to learn the function representing the mapping from X to Y. The X is encoded at the beginning. You can also consider quantum data sets. So this was something which was on the lower corner here in this picture I showed you in the very beginning of the different overlaps, right? So this would be a quantum machine learning model applied to quantum data, where actually your input is already a quantum state, right? So basically you replace your classical data encoded in this unitary, you replace the pink blocks directly with the box that prepares this specific quantum state. And then you can also do, let's say, classification in the spirit of entangled state versus separable state, for example. Anyway, but this is just an excursion. We are focusing on the classical case usually. So we have, as I said, the state encoding. We have this parameterized unitary. You take the measurement, and your yi, so your prediction of the x, is given by the expectation value of your data-dependent and parameterized observable in the initial state. Right? So this is a value you're computing with the quantum computer. This is an expectation value. You're actually not, okay, do you know if we get this exactly or just an approximation of this one with the quantum computer?
What do you mean?
So, okay, what I want to say is, with a quantum computer, you always produce shots. You're not exactly getting the expectation values, but you're running shots. Right? You get basically out of this, at the end here, you get bit strings. Right? So zero and strings of zeros and ones. From these bit strings, you estimate the expectation. And you need to have a certain number of shots to have a good approximation of the expectation value. This is a limitation. Even the quantum computer would be noiseless, right? You got that, you still have shot noise. Right? You never get this quantity exactly because you can't manipulate the final measures. It's not necessarily a problem because you can have a large number of shots, and then you have a very good precision. No, right? But in principle, it's good to remember always what sort of errors affect these quantities. One computer, one is 100 shots, the other one is currently errors and so on. And then this output of the quantum computer is going into a classical algorithm. Or classical computer is computer does certain things with it, comes up with a new suggestion for an updated set of parameters, which are now changed in the box, right? And then this extent is just normal machine learning cycle. You make one run, you get a prediction, and you compare it with the loss function. And based on this comparison, the optimizer proposes a new set of parameters, and then you ideally converge to so the question was if you can create a set optimization. Yeah. So it's created to set, but there are also based on objects. This is the same, like in classical machine learning, you have a ton of different optimizers, and this is basically the same. So sometimes what you need is not just one expectation value, but you need several expectation values with slightly shifted parameters so that you can estimate the gradient, right? If you tune the first parameter, let's say plus minus epsilon, right, you get two different expectation values. And from this expectation, from the difference of these two expectation values, you can estimate the gradient in this direction. This is exactly what was done, principle was done for classical hardware. So it's some sort of finite difference approximation of a gradient.
The quantity of this mass, I think that's four facts. It's being held from classical systems.
So the question was, okay, the first part, like the quantum computer is doing the forward pass, the optimization happens on the classical computer. What you call now heavy lifting, and heavy lifting is a bit okay. Some would call it the optimization procedure, actually heavy lifting. But so in reality, depends on your architecture. But classical computers are very fast, right? So you have to go to very large system sizes, or you see the advantage of the quantum computer. Now we have the little situation that the quantum computers are very small, right? You are the field, right? And so in this regime, you would typically expect that the forward pass takes longer than. Good. Do I speak too fast? That's that. So that's the pipeline. And now these are a couple of references about the first part I was showing you, right? Which was basically introduction to statistical learning theory, just a classical thing, and a little bit about parameterized quantum circuits. How, let's say, the setup is very parallel to what you do in classical machine learning, that you have a quantum model, a parameterized quantum circuit, instead of a neural network, let's say. And some people actually call this thing here just a quantum neural network, right? There's this term quantum neural network, and often people mean this thing here as quantum neural network. I'm not using this because this doesn't look anyhow like a neural network, so for me, it doesn't have anything in common with a neural network, so I just call this a parameterized quantum circuit. But I mean, these things are just names, right? It's just that we use the same names. All right. So the next step would be to go a little bit into examples. So now we did already 1 hour. We want to have a 5-minute break? Yes? Okay. So we have a 5 to 10-minute break, and I'm going on towards in 8 minutes or so.
There is how long it takes. That's it. Get level. Also have certain checks. Speed. Bottom line starts here with a long overhead, we call it very small slope. Test line starts here with a very small overhead, and as some point cross that needs to be. But now, if the cross point is, let's say, system size of one of the first, if you really have to go big, all the particles need to be developed. And it's still very hard to find a problem where you get into together. Yeah, it's two aspects. It's pretty constant. It's overhead being a very large small point. They cross, and they find this cross point, and the problems of variables. Well known years from polynomial, so this requires exponential numbers. Now, if you want to compare design exactly with the representation, this is comparison. Last basic orientation. This is somewhere close to the same, but some approximation. Then there's called QA.
Currently, it's believed that you have P, you have EP, you have EQP, then you have QA, and then you have NQ. Which believes that you have QA, but the R is hard. But this is really debate about this, so it's good. It's a national advantage. But you don't expect the direction. Yes, the next advantage. And there are many problems which are just actually solved. Because the end problem is the problem is finite, not graph infinite size, it's graph 1 million nodes. It's still complexity does look there. What is this? Things, I mean, what you do, that is short about. And I think this one shot is a new generation of producers, right? You want to produce new cash and stuff. The one shot is producing new. But in the triple case, this was in the category that you need number of people to do it. Was So, hello everyone. We are going to continue. So, have there been any questions coming up during the short break? Questions? So the target for the next, let's say, half an hour is to go through some examples. Mainly two, to be honest. We start with one, and see how far we get. And this is called data re-uploading or Fourier model. So it's a model where you re-upload your input data, basically this one, right? So you have certain layers, and you don't have first X, then theta, but here you have them interleaved, right? One layer is both encoding theta and X with an encoding unitary, but then comes another layer with the same X encoding, but a different theta encoding, let's say. Right, and then you go. And then you go through these layers, right? L layers. So you have these data re-uploading. You always put the data again on the quantum computer. Here's again the measurement of the observable. You can write it as an equation, but this is exactly the same, which is written here. Maybe one thing to note, I guess you already saw this previously, but the equation notation is mirrored in comparison to the circuit notation, right? The first gate that is applied in the circuit representation is to the very left, whereas in the equation representation, the first gate that is applied is to the very right. So you see here's 1, here's L plus 1, it's the other way around. So this is not, this doesn't has a very good reason, right? This is just what people started to do and no one was able to change it, basically. So, but yeah, circuits are always read from left, whereas these operator sequences are read from right. But this is something most people are familiar also from classical matrix calculation. Okay, why do we do this? This reiterated upload of the data actually helps to increase the expressivity of the model. So this is now a model which is about function learning, right? So this is regression, not about classification. We have a target function, and we want to choose the parameters such that circuit approximates the target function. And the theoretical goal is to write this circuit as a Fourier series. So this is just the expectation value of the specific observable with these unitaries sandwiched, right? Initialized in the zero state in this case. And we want to write it in a form where we sum over all frequencies. So it will become clearer what these frequencies are, but these are float numbers, real numbers. Coefficients that depend on the parameters, and just the x dependence is only via these imaginary exponential multiplied with the frequency. And I guess who has seen Fourier series already? So yes, this is very famous, right? So I guess most people have seen it. Is this true? Thanks. And as you might know from your theory about Fourier series, is that they are universal. So certain functions, typically you consider square integrable functions. So you have an interval, you have functions such that the integral over the square of the function is finite. This is called a square integrable function. Or any function you can imagine is typically square integrable. So it's very hard to come up with non-square integrable functions. And who knows an example of a non-square integrable? Huh? Of a non-square integrable function. Can I go here? You know? Okay, 1 over x actually is not so difficult, right? You have interval 0 to 1. The function 1 over x looks like this, has a infinite, like a what's it called? It's getting to infinite when you go close to 1. Now it's not exponentially increased, but it's like a definition pole. Huh? So singularity. So it has a singularity because it's diverging to infinity if you go close to 1. And 1 over x is actually a limit case where if you compute the integral from 0 to 1, square of it, this is an infinite quantity. So this is not a square integrable function. It's okay. Maybe later. Thank you. But yeah, many functions can be represented by such Fourier series, and we are going to show that this model allows for this representation, and this tells us that we can actually represent a very large function class with such a model, right? So this is a universality result. But now we have to do a little bit math here now, so I hope you will come with me through these set of equations. So first of all, the ij is the eigenbasis of the Hamiltonian in our case, right? So and V is the transformation that maps the computational basis to the eigenbasis. And we write the observable as a generic expression over this specific basis ij. And now we plug in, so we have a Hamiltonian, right? Again, this is the Hamiltonian appears in the exponential, right? So the unitary is e to the I h, right? And taking into account these basis transformation, which diagonalize the Hamiltonian, we can get them out of the exponential and basically know that the unitary is the basis transform of the exponential, the imaginary exponential, where lambda now is the diagonalization of h, right? So lambda has the eigenvalues of h on the diagonal. Who knows about eigenvalues and diagonalization? Huh? Eigenvalues? Yeah. Yeah, very good. So two people, I think that it's a very generic method or so now we plug in this expression here. We put the v's into the w's actually. So we absorb the v's into the w's because the w's are just a generic expression, not important what the w's are actually, right? And what comes out then is this equation. So we start with 0. Okay, it should be a 0. So that's okay. I'm not following my convention. So we start with the 0 state. It should be a 0. And now we sum up all entries of W and contract it with the next W. Right? Now what's happening with the U's? Because the U's, the diagonal, the J1 here is the same as the J1 here. Right? And the factor which comes from the U is just this e to the I lambda J1, which is the eigenvalue. And this we do when we go to low values. This we do for each of the U's which appear here. So we have a train of W's which stay there, which are, let's say, matrices that are contracted with each other. So these indices are all sum. So basically, this is just a very long train of matrices that are multiplied with each other. And we have spectrals with the eigenvalues just appearing here. And now we introduce a little bit of notation. So we put together a multi-index. So we put these J1 to Jn into a bold-faced multi-index. We call the set of all these multi-indices these square brackets with the power of d with the power of L. So this is just notation. And we introduce the mu's here, which are the sums that are appearing in the exponential. So we have the exponential, we have the mu's appearing here, which is just containing the information about the eigenvalues, right? And then we have our x, which is the data encoding. Then we have this train of these matrices, which are not very important for us. We just carry them with us. And this is the final form already. So there's one thing that's happening from here to here, because as you know, f is not this expression, but it's actually expectation value, right? So it's 0, u, a, u dagger 0. You remember this from the previous slide? So you have 0, u, a, u dagger 0, right? And now you replace the a with a sum over all aij, the cats and grass, okay? And then you end up with this expression with an arbitrary I on the right side, and the mirrored expression with a 0 q dagger j on the other side. Right? So you have this guy and let's say a mirrored expression of this. Turn everything around and replace the I with a j. And if you multiply these two things together, then you end up with this expression, where you not just have the mu j, but you have a mu k and a mu j here. So the mu j is coming from this expression, and the mu k is coming from the mirrored expression that you put into the other side. Right? So it's not important that everyone gets this, but I mean maybe a few. And these are the frequencies. These are going to be omegas. So the only x dependence is just exponential, right? And all the parameters are combined into the CW, which is a crazy sum over a's, and these a's contain all this crazy string of w's. So it's not important what precise expression this is. It's just important that the only parameter dependence, so on the thetas, is going to be in this coefficient, and the only x dependence is going to be in this exponential. Right, so this is what's happening there to separate these two factors. And with crazy expressions, but this is really fun. Does it make sense? Who has seen something like this before? No, maybe not, right? Anyway, so this is something, if you have time, you can always try by yourself. Right? It's just linear algebra. It's not so difficult. I mean, it's unhandy because you have very long expressions, but in the end, it's not that difficult to divide. And here I want to show you a little bit what you can do with these data uploading circuits. So let's assume our target function is this black line here, right? Which is like a sort of combination of sine and cosine. I don't know which. And if you don't do data uploading, right? So you just have a 1 qubit circuit, which is just encoding x for one time. You actually can just encode or produce a plain sine function. So you cannot really approximate this guy well. Right? You see, it's a very bad approximation. But now, as you do, let's say, 3 data encodings in a row, you can actually represent degree 3 Fourier series. So it's a superposition of up to 6 sine functions. I mean, if you know a little bit about Fourier theory, it's not just one sine function, but you add a couple of them, and then you can actually produce something which looks much closer to this black line. And if you go to 5, you actually can get it pretty precisely. So this is actually an experiment which was done in this paper here. And so this is sequential reuploading. You can do also parallel reuploading, where you don't apply x's in a row, but you apply them in parallel. Of course, this has a bad scaling, right? So here you need as many qubits as how often you want to apply x. That's not really good. It's much nicer if you can have it in this linear form. But you get very similar results. So, yeah. Yes. Yeah. Yeah, so the question was, I can go a bit more to say about the parallel encoding. And you said the parallel encoding is very hard. I mean, so, I mean, maybe you know more about classical parallelization and so on than me, but the bad thing about this parallel encoding on a quantum computer is that the number of qubits needs to scale with the number of parallel executions you have to do. This is something which is again a base of this. So basically, it's like, I mean, okay, we'll come to an equation later. Okay? So it's basically this here in equation form. You will see. Yep.
About the rate of movement, how I think, for instance, that I have things that
So it's not a re-uploading where I stop the application and start again with the re-uploaded. This is not what's happening. It's during the computation, you have several repetitions. So your these little boxes, the unitaries, which depend on X. Right? So for example, this Hamiltonian encoding, which we saw before, is a good example of this. And you have a set of gates which contain parameter, followed by a set of gates which are X dependent. Again, a set of gates which are dependent on parameters, again followed by. So this re-uploading happens in one go actually. Just as you run this forward pass, data is recorded. So this is the equation of the parallel encoding. Your UE is just a tensor product of single qubit exponentials where you apply the exponential of one of these sigmas, and the sigmas are again from the set of Pauli matrices, right? So you have e to the I Pauli matrix, and you apply this on each of the qubits. So basically, each of these things here is exponential of a Pauli matrix, and the Pauli appearance exponential could be either x, y, and z. And the x here has nothing to do with the little x here. Right? The little x is referring to the data, and the x here is just referring to the Pauli. So basically, okay, the little x is here, and the sigma I could be a big x, could be a big y, could be a big z, right? So this is the parallel encoding. You apply this to each qubit in parallel, and then you have big blocks of W's which are before and behind this one. And this one looks, for example, like this. It's not very important, but it's just a huge circuit. Does that make sense? Yep.
There are still within that that's the monetization of things. It is now we see the same data.
Yeah. So very good question. The question was, okay, if I do this reloading, do I have the risk of overfitting the model, right? Because the model sees the same data very often. And actually what we are going to see in a second is that the number of iterations, number of layers is connected to the Fourier degree of the Fourier series, right? And this is exactly overfitting. If you choose a too large Fourier degree, you're going to overfit it, right? If you have, let's say, 100 points, and you fit a degree 100 for series, you actually hit all of these 100 points, but the actual trend, which is in there. So that's a typical like parameter. Yeah, if you have too many parameters, right? You don't care about the realization and so on. You have the risk. So what I wanted to quickly go through here is how do we end up with the set of frequencies, which is determining the fully degree model. And basically, this is the Hamiltonian, right? The sum over these set Q's. So basically, okay, it's a little bit of a jump name, but UP, as I said before, or no, actually. So one thing is that you diagonalize U, right? So you find the matrix V such that this representation here is diagonal and is the same as U. And you can do this because it's easy to diagonalize the product of Pauli strings. If you diagonalize the tensor product of two matrices, you can diagonalize the two matrices separately from each other. They are not dependent anymore. And these matrices are very small, just 2 by 2. So it's super easy to diagonalize the matrices. So it's super easy to get the lambda. Right? And this lambda actually just have form of sum over these set Q's. Because you're going to diagonalize each of these x's or y's here and here in a way that it's going to be that it's looking like a set matrix. And now the question is, what are the eigenvalues of the sum over set Q? So has someone an idea about how these eigenvalues look like? So okay, sorry, how does set Q look like? How does set look like? How does set look like? The Pauli matrix set. So it's a diagonal matrix having a +1 in this corner and a -1 in the other corner, right? It's a very simple +1, -1. So these are the two eigenvalues of set. And now you're summing up R values where each of the value can be either +1 or -1. So what are the values we can achieve by this? Can go several steps upwards and then several steps down again, right? Because we're either going +1 or -1, so we're jumping on a lattice with distance 1, right? And if we sum up, if all the set Q's are +1, then actually this is R, right? Because we summed up R times +1. And if all the set Q's are -1, we are -R. So this sum over set Q is between -R and +R in integer steps. -R plus 1 up to R -1R. And now there's a factor of 1/2. So we're from -R/2 up to +R/2 in half integer steps. Yeah, this is the I is actually taken care of this computation here. Right, so this was what we did here. So the lambda here is in this specific example the sum over set Q's. Right? The eigenvalues of this one are what I just said, something going between -R/2 to +R/2. And the I is actually just staying there in the calculation. So the I is always staying in the exponential, and the question is, the set of frequencies is just determined by the values which I can achieve by adding up these eigenvalues. So the I is actually always staying here in the computation, doesn't change much. So, but yeah, just to say, the lambdas basically are going between -R/2 up to +R/2, and this is how you can write it, right? The P, if P is 0, then you are -R/2. If P is R, then you are R -R/2, so +R/2, and you're taking half integer steps there. Oh, actually, you're taking integer steps there. Apologies. Yeah, anyway, it's also not an important detail, but I think you're taking integer steps here. But the idea is, okay, based on this, you can write down the set of all frequencies, and this is going to be, again, -R until +R in integer steps. And these are now exactly the R different Fourier modes that you can represent with the series. So the degree of the Fourier series you can represent with this circuit is R. R parallel representation 5 allow you to encode a degree 5 Fourier series. Okay, so this is direct, the direct connection, and then it's going to this overfitting question. If R is too large, you probably overfit. So yeah, this was hard computation. Now I have a second computation which you can do on your own. So what's the time? Okay. So and after this we're going to finish. So but we still try to do this. Now we're looking not at a parallel picture but on the sequential picture. Okay. So the U looks like W exponential, W blah 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 exponential, where you're always using the same sigma here. So in this case, please assume sigma to be just set such that this exponential is already in diagonal form and is given by e to the I lambda over 2, with lambda being 1/2, sorry, e to the minus I x lambda, with lambda being 1/2 times z. And now the question is, to compute this frequency spectrum. And so, as I said before, the mu j's are sums over lambda j's, right? So you need to find out what is a good how can you write down mu k, dependent on k, right? What is the form of it? And then you take two of them together, one with k, one with j, and take difference and see what comes out of this. And there's a hint. First, you have to consider what is actually d in the setup, and what are the values of these lambdas. So has someone an idea what big D is in this setup? No? Come on. Someone? So, okay, what are the lambdas? Actually, it's written on the slide. Huh? I didn't understand it. Yeah, but what are the values? Like the precise values? Is it 24 or minus 7? Or maybe plus half, minus 1/2. Okay, right, they're here. So these are the lambdas, and now from this you can infer what T is. So how many different things do we have? 2. Okay, T is 2. Lambdas are either I or J, right? So now think about you picking a multi-index J, right? J, and summing up this train of lambdas where each of the lambda can be either plus 1/2 or minus 1. Okay, now give you 5 minutes, 7 minutes to think about this.
You write in the slides or you need a whiteboard?
No, if possible, just on top of the slide.
Just on top of this one. Down, down here. Okay. Yes, thank you.
Which one?
Some pictures.
No, I have to, this one?
Yeah, that means you have to, or if the slides can be sent here, then we can project it from there, then we can write. This one picks from here.
So it's not possible?
It's not possible we can write. Because this will not pick from here.
So
Unless the slides come here, then you can write there. Or you use the whiteboard.
then we can switch back.
Yeah, I see it. So you can use the whiteboard and you can write. Eraser, pen, those are all pens.
Just use this.
Yeah, that's the area one. These ones are all pens.
Yeah. Sounds good. And how do I get back to the other screen?
Get back with this. So if you want to go back, you have to.
Just close it. Here.
You can just go by, if you not come down here.